develop Java programs, you will want an IDE, an integrated development environment that has tools that let you edit, compile, and run your Java programs. There are a lot of IDEs out there, and I'm going to focus in on two of them. The first is Genie, a lightweight IDE. It doesn't have a lot of features, but it's easy to start with. The second one is Eclipse. It's a full-featured IDE with lots of tools and utilities to support Java. Both of these are available for Windows, Macintosh, and Linux. Let's look at Genie first. The first time you start Genie, you're going to have to make one change in the preferences. Go to the Edit menu, choose Preferences, and the Terminal submenu, and make sure that this option, Execute Programs in the VTE, is checked, and then click OK. You only have to do this once. Now, let's open an existing program. I'm doing this on a Linux system, so the File Open dialog box doesn't look the same as the one on Windows or Macintosh. Once you have your program written, select Compile under the Build menu, and in this case it finished successfully, and then select Execute from the Build menu, and there's your output. It works. You can clear the output in the terminal by right-clicking and selecting Restart Terminal. Let's try making an error on purpose to see what happens when Java encounters an error. We're going to remove the semicolon at the end of line 8. Now, if I compile the program, you'll see that it expected a semicolon on line 8. It points out where it found the error, and also gives the little red underlines on the line in question. In the interest of cleanliness, I'm going to put back the semicolon and I'll recompile. You don't have to save the program before you compile. Genie will do that for you automatically. There, that's much better. It compiled successfully this time. By the way, you can get a version of Genie for Windows that installs to a USB drive so that you can take it with you anywhere you go. Now let's look at Eclipse. When you launch Eclipse, it will ask you where you want to save your work in a workspace. Take the default. You'll see a welcome screen, which you can close. Let's create a Java project and call it Example. We'll use the project folder as the root for the source and class files. Go to the next page and accept all the defaults. We now need to add a class to this project. So from the File menu, we will say we want a new class. The name of it will be Example with a capital E, and we will want to have a public static void main. Make sure that's checked. And there's the template where we can add our code. The first thing let's do is add a comment that tells what the program does, and the author and date. Then let's add our Java code by saying system.out.println it works! Exclamation point, and a semicolon at the end of the line. Now I can run the program. When you run the program, it'll ask you if you want to save. I'm going to say I always want to save before launching the program. Click OK, and there's my output. It works. Again, what happens if I make a mistake? If I make a mistake, let's say I get rid of the semicolon here, you'll notice that a red X shows up. If I hover over it, it will tell me what my syntax error is. If I try to run the project, even though there's an error, it'll ask me, do you want to really proceed? I can say yes, let's proceed. And then I will see in more detail what the error is. It'll tell me that line 10 has a syntax error, insert a semicolon to complete the statement, and you'll notice the little red underline there. Let's put back the semicolon, the red underline and the red X disappear, and I can run my program again. Eclipse keeps track of all the projects you have opened in the panel at the left. If you want to delete an entry from the list, right-click the project name and select Delete. Make absolutely sure that the Delete Project Contents on Disk is not checked. The project name will be deleted from the list, but it won't be deleted from your disk. There's a lot more to Eclipse, but this should be sufficient to get you started. Let's talk a little more about bits and bytes. As the book tells you, a byte is 8 bits or binary digits. Here's a byte in binary. If we interpret it as an integer, it's the number 109. If we interpret it as an encoded character, it's the lowercase letter m. If we interpret those bits as a programming instruction on a 6502 processor, it's the instruction to add 2 numbers. This last part is important. Each pattern of bits is a different instruction to the CPU. This is called the CPU's instruction set. Every different type of CPU has a different instruction set or architecture. That means this pattern of bits, which is an add on a 6502, might mean jump to a different part of the program on an ARM processor or load an accumulator on an Intel processor. When we write a program in a high-level language, it has to be translated into the bits and bytes for the CPU that's going to run the program. That translation process is called compiling, and for most languages you need a different compiler for every architecture. The people who developed Java took a different and interesting approach. Instead of multiple versions of the compiler, there's one compiler that compiles to bytecode, the instruction set for an idealized machine whose architecture is optimized for Java programs. This is the JVM, the Java Virtual Machine. Now, instead of having to write a new compiler that generates bits and bytes for every different architecture, which is very difficult, we write a program that takes the bytecodes and implements them for the hardware we're running on. This is a much simpler task. Here's the workflow. You write your program in Java, you compile it to bytecode, and then run it on the JVM, the Java Virtual Machine. Once you have a working program, anyone with the Java runtime environment, which is the bytecode interpreter, can run it. Here's a typical first program, which we'll go through in detail. At several points, we'll be telling you to take our word for things rather than go too deep into detail. The lines beginning with /* and ending with */ are a comment. You use them to let other humans know what your program does. Java ignores your comments. They're for people, not computers. In this course, I will ask you to put comments at the beginning of all your programs. The comment should tell what the program does in some detail and should have your name and the date. All Java programs must have at least one class. By convention, class names begin with a capital letter. The word public tells who can access this class, and you'll learn more about that later in the course. Java uses braces to indicate a block of code, sections of code that belong together. Every opening brace must have a closing brace. Within the class, you define methods, which describe the things the class does. Methods are a lot like mathematical functions. The words public static void are, for now, a magic spell that you need to chant to make Java happy. Main is the name of the method. Whenever the operating system runs one of your Java programs, it looks for a method with that special name and starts by executing that method. By the way, Java is case sensitive. If you were to name that method main with a capital M, the operating system wouldn't find it when it tried to run your program. The parentheses and string square bracket args are again a magic spell. For now, let's oversimplify by saying that this allows you to give information to a Java program when you run it from the command line. The body of the main method consists of two lines that both make calls to the system.out.println method. This method takes a string as its argument and prints it to the output, your screen, on a line all by itself. The ln at the end means print and give a new line. The string must be in double quotes. The semicolon at the end of the line is required. It tells Java that the statement is finished. The next line is another statement that prints another string. Again, it needs a semicolon at the end to say, this is the end of the statement. These are the building blocks that you'll find in every Java program that you write in this course. There are many different styles for writing Java code. Depending on the book you're reading or the company you're working for, you may be asked to put opening braces on a line by themselves, or, as in the book we're using, put the braces at the end of a line. You may be told that when you indent code, you should use 4 spaces or 2 spaces. When you indent, do you set the development environment to insert a tab character or to insert spaces? These choices and more are part of what's called a style guide. For this course, ask me if I care about which style you use.
Do you care?
No, I don't. Choose the style you like best and use it consistently. There are some things I will insist on. First, your programs must be indented properly, no matter which spacing you decide upon. Your programs must have comments at the beginning that tell what the program does and that give your name and the date. One thing almost all style guides agree on is that each line in a multi-line comment begins with an asterisk. Most development environments will insert this asterisk for you automatically. Again, you must indent properly. Don't mix styles, and whatever you do, don't throw all the rules out the window and go for an artistic effect. Choose an indentation style and use it consistently. Here's a program that prints a person's approximate age in days. If we compile it and run it, it works great. But each part of the output is on a separate line because we used system.out.println, which prints the information and then gives you a new line. If you don't want a new line, use system.out.print instead. Let's print the first part of the output without going to a new line. We'll change this println to a print, recompile, and run it again. Now our output appears on one line, but it's all bunched together. To make it look better, we need to put an explicit space between the words and the numbers. Notice that the space must be inside the double quotes. Let's recompile and run. There, that's better. The last line of output, the number, is produced with system.out.println. This is absolutely essential. Why? Let's change this println to a print. Recompile and rerun. When we run it from Genie's execute command, it seems to be okay. But let's say someone doesn't have Genie and runs the program directly from the command line. They run it by typing Java and the name of the program, and they get this as a result. The next command prompt appears on the same line as the last output, and that is incredibly ugly. Let's change that last print back to println and recompile. Now let's go back to the command prompt, clear it, and try running the program again. And this time the next prompt shows up on a new line, and that looks much better. And that is why you should always use system.out.println for the last output of your program. The exercises in Chapter 1 use Java as a glorified desk calculator to do arithmetic. After you learned arithmetic, you moved up to algebra, where you used variables. In a similar way, we're now going to move from simple calculations in Java to using variables in Java. It's similar but not identical because variables in Java do not work exactly the same as variables do in algebra. First, we have to declare variables before we can use them. A declaration gives the name of the variable and its data type. Here are two declarations, one for an integer variable named age and another double floating point variable named price. When a numeric variable is declared, you can think of it as an area of memory that has that name for a label. By default, numeric variables are set to 0. You can assign new values to variables. Let's assign a value to age with this statement. The way Java does this is to look at the right-hand side, figure out what it works out to, in this case 23, and then that is stored in the variable on the left-hand side, replacing whatever used to be there. It's also possible to declare a variable and give it a value in one step. In this case, the right-hand side of the equal sign works out to 8, and that gets stored in the newly declared variable price. What happens with this assignment statement? We always start off with the right-hand side and figure out what it works out to. So let's take a piece of scratch paper and figure out what the current value of price is. It's 8.00. We multiply that by 0.05 and end up with a result of 0.40 for the right-hand side. Now and only now do we look at the left-hand side and find that variable tax is to receive that value. To drive home the point that variables in Java don't work like the ones in algebra, let's look at this set of two statements. At the end of the first statement, age has the value 23. Now let's look at that second statement. In algebra, that doesn't make any sense at all. 23 doesn't equal 24, but again, this isn't algebra. Instead, you're going to follow the rule. When you see an equal sign, you're going to pull out a piece of scratch paper and figure out what's on the right-hand side. What's in age right now? It's 23. We take the 23, add 1, and the right-hand side works out to 24. Now and only now do I look at the left-hand side and say, who's getting that 24? The answer is age is getting that 24, so age gets 24 and the old value of 23 is replaced. What we've done here, by the way, is called incrementing age. You'll see patterns like this all the time in Java. You read it as x is assigned x plus 1 or x becomes x plus 1. And again, you'll see this a lot because it's very common to have computers do counting. The moral of the story: whenever you see an equal sign in a Java statement, you read it as variable is assigned value, or variable becomes value, or variable gets value. You go to the right-hand side first and figure out what that value works out to. Once you have it completely worked out, then the variable on the left will get that value. The book talks about the float and double data types. What are they, and where do those names come from? In general, a floating point number is one that has a decimal in contrast to integers, which are whole numbers. As to the origin of the term, a bit of history. Back in the old days, when computers were primarily used in the business world, common business-oriented programming languages let you specify that a value had a fixed number of decimal places to the right of the decimal point. A fixed decimal 2 value would always be represented with exactly 2 decimal places, no more, no fewer. The business world was happy with this. Scientists, not so much. To do scientific calculations accurately requires varying numbers of decimal places. In other words, the decimal point can't be fixed in one place. It has to float according to the demands of the calculation. And that's where the term floating point comes from. In Java, the float data type specifically means a representation that takes up 32 bits, can represent numbers from the range 10 to the minus 38 to 3 times 10 to the 38th, and has 6 to 9 digits of accuracy. However, that's not a large enough range or precision for some scientific calculation. So there's another data type called double, which uses twice the space, 64 bits, and gives you a phenomenally greater range and almost twice the precision. In fact, double is often called double precision for that very reason. In Java implementations, the default for values is a 64-bit double. 14.52 would, by default, be double. If you really want the lower precision float, you have to follow the number with the letter F in either upper or lower case. Consider this program, which calculates a person's approximate age in days. There's nothing wrong with it. It works great when we compile it and when we run it. It says that someone who's 21 years old is about 7,665 days old. However, these variable names y and d aren't particularly good. If we had a very long program with lots of variables, we might not know instantly what D stands for. Days, discount, deposit, or what? You should always make your variable names as meaningful as possible. In this program, changing Y to years and D to days makes the program much more readable with a minimum of effort. Suppose we wanted to be a bit more specific and rename the variables as age in years and age in days. We could rename age in years as AIY and age in days as AID, but that would be a terrible idea. First, AIY is meaningless, and second, AID sounds more like a call for help than an age. If we spell out the name entirely, we get names that are long and difficult to read. How then do we handle multi-word variable names? One solution is to use underscores between the words of the variable name. This is called snake case because the underscores make the word look sort of like the segments of a snake's body. Another method, which is the one that is used by convention in Java, is camel case, where each word after the first is capitalized. It's called camel case because the capital letters are reminiscent of the humps of a camel, if you use a lot of imagination. In this course, we'll expect you to use camel case for all your multi-word variable names. To summarize, always use meaningful variable names. Don't make them too short. Don't make them ridiculously long. Make them meaningful and just the right size. Let's take another look at the program that calculates age in days. Again, there's nothing wrong with it. It does exactly what it says it will do. However, if someone isn't 21 years old, let's say they're 25, They would need to edit and recompile the program to get the correct answer for their age. Wouldn't it be nice if we could ask the person using the program to enter their age from the keyboard? Then it would work for anyone of any age. That's what we're going to do in this version of the program. In order to get user input, we need to use a library called scanner, which is in the java.util package, and we have to import that into our program. This import and any other imports you do must be at the beginning of your program. On line 11, we have an assignment statement. Let's look at the right-hand side. It says to create a new scanner object that reads from system.in, which is the name of the standard input device, your keyboard. This object is assigned to a variable named input. Input is not a reserved word, it's a meaningful name. Just as we have to precede variables like age in days and age in years with int to tell what type of variables they are, we have to precede the variable name input with its data type. It's a scanner object. Here we're using print instead of println. This prints the text without going to a new line because we want the input cursor to appear on the same line as the prompt, not on a new line. Second, we have a space before the closing quote of the prompt string. This puts extra space between the input prompt and the input cursor, and it just looks better when you run the program. In the next line, we get down to business. The right-hand side invokes the nextInt method of the input scanner, which reads the next integer from the keyboard. This gets assigned to age in years. In the next statement, we take that age in years times 365 and assign it to age in days, and conclude the program by printing out the results. Let's run the program. Compile it first, and then run it. If your age in years is 30, that's the approximate number of days. Let's run it again for someone who's 47 years old. And now we have one program that will work for any of our people who are using it. You may be wondering, what happens if you run the program and instead of entering a number, you enter a word like FIVE? Answer: the program crashes. The error message says you have an input mismatch exception. There was a mismatch between what you typed and what nextInt wanted. For now, don't worry about handling this sort of bad input. We'll learn more about exceptions and how to handle them later in the course. In summary, to get user input, you have to import the scanner class. You have to create a new scanner object that reads from the keyboard and assign it to a scanner variable, and then use that scanner's nextInt method if you need an integer. Or if you need a double value, use nextDouble instead of nextInt, and that's nextDouble with a capital D. Here's a program that asks for your age in years and prints out your age in days. We're using 3 separate statements to create the output. The first 2 use print, not println, so the output will appear on a single line. Let's run the program and see that it works. That's a lot of work to create a single line of output. There must be a better way. One better way is to use a plus sign. Let's go into JShell, a tool that comes with Java 9 and above. It lets us try out Java expressions without having to write a whole program. We know that plus works with integers and with doubles. It also works with strings by tacking them together. So the string door plus the string bell results in the single string doorbell. What happens if I try to add a string and a number? For example, 2 plus the word space dozen. It works. That's because Java converts the number 2 to a string and then tacks on the word dozen. Now that we know that this works, we can go back and modify our program. Instead of these 3 lines, we'll make one line and use a plus sign to join all the parts together. We need to put the blanks in ourselves to make sure they appear in the output. Let's compile and run, and it works great. Here's a program that lets you enter a price, and it tells you the amount you pay with a 15% discount. Let's run the program with a price of $25. Looks good. Now let's run it again, and this time put in a price of $20. That output isn't quite as lovely. And if we run the program with an initial price of $4.90, the output is really ugly. To solve this problem, to get exactly 2 digits after the decimal point, we need to use string formatting. Let's start investigating formatting by going back to the age and days program and change the output to this. Instead of println, we're going to use format, and we're going to have one string that is about $d days. What's that $d? It's a format specifier. Whenever you see a %, think of it as a placeholder where a value will go into the string. The D specifies that we want an integer to fill in that placeholder. The letter D is used for integers for historical reasons, by the way. After the string, we give the variable that fills in the placeholder. Days will fill in this $d placeholder. Just like print, format does not give us a new line. So we have to explicitly give a new line character, which we write in Java as \n. Let's compile this program. And run it. And it works great. You can have multiple placeholders and specify multiple variables to fill them in. I can change my output to say placeholder years is about placeholder days, and then provide the variables that fill in those placeholders. Compile, run it again, and get my nicely formatted output, all without needing a plus sign anywhere. Let's return to the discount program. To build a format specifier for doubles, you use the F specifier and tell how many digits you want to the right of the decimal. Instead of println, we're going to use format. We're going to say $.2f, which says I want 2 decimal places in my double placeholder. We'll also put in our new line, and there's one other thing we need to do. We don't want format to think that this % is part of a new placeholder. To tell format that this % is not part of a placeholder, that we really do want a % in our output, we need to put 2 % in a row. Now that we have our format string with its placeholder, we give the variable to fill in that placeholder. Let's compile that. And when we run it with our $20, we get 17.00. And when we run it with an initial price of $4.90, we get $4.17. You'll notice that format has rounded the number for us. There are many other format specifiers, and you can add information that tells how many spaces a number should take up. This lets you produce output where everything lines up nicely. Here's a URL where you can get the details about formatting. There are three types of errors that you can make in your Java programs. The first type is called a syntax error. A syntax error happens when you say something that's not grammatically correct in Java. In this program, I've said 34 plus times 8, which doesn't make any sense mathematically. And when I compile the program, the compiler shows me that it is indeed a syntax error. It also points out where Java got confused. You can have another kind of error called a runtime error. This happens when your program tries to do something incorrect when it runs. For example, if I try to evaluate 42 divided by 0, that's grammatically correct. I have a number, a division sign, and another number. And Java compiles that just fine. But when it comes time to actually run that calculation, I get an error telling me that I have an arithmetic exception. I'm trying to divide by 0. It also points out which line was executing when the error occurred. These two types of errors are usually pretty easy to find. Syntax errors are the easiest because the compiler points them right out to you. And runtime errors are fairly easy as well because once you run the program, you see the error front and center. The third type of error is called a semantic error, which means you told the program to do something, but it wasn't what you wanted it to do. For example, if I want to find out approximately how many days there are in 21 years, and I run this program, 386 is nowhere near the correct answer. The problem is here on line 7. Instead of multiplying by 365, I added 365. That's not a syntax error. A plus sign is just as valid to do as a multiply. It's not a runtime error because adding 21 and 365 won't cause the program to crash. It's not what I intended to do, which is why I got the wrong output, and that makes it a semantic error. These semantic errors are, in general, the hardest ones to find because it's only when you look at the output that you realize this is not what I intended, and then you have to go back to your program and figure out what you did wrong. Sometimes Java will appear to point out the wrong line for a syntax error. Let's look at the compilation of this program. Java says I have an error on line 7, but if I look at line 7, everything looks perfectly okay. The error is really here on line 6, where I put a plus sign instead of a semicolon at the end of the line. Why did Java say the error was on line 7? The answer is because of the way Java parses your programs when it compiles them. Have you ever buttoned your shirt and found out when you got to the bottom that you're out of buttons? Now, where did that error start? Did it start at the bottom, or was it somewhere up further on? The answer usually is that it was up somewhere near the top and you forgot a button or buttonhole, and that's why you're out of buttons when you get to the bottom of the shirt. Java works in somewhat the same way. It's on line 6, int is okay, this is a great variable name, equal sign is cool, 21's a normal integer, a plus sign is perfectly valid here, and oh, I'm at the end of the line. There's nothing after the plus sign. Well, maybe the other operand is on the next line. Java goes to the next line, and when it finally gets to age in days, it says, wait a minute, I can't possibly make a valid Java statement out of this. The compiler throws its hands in the air, gives up, and says, okay, the error must be here on line 7. This shirt is out of buttons. The moral of the story: when you get a syntax error, Java will give you the line number where it gave up, where it could not go any further and make a valid program. This means that your error may be on that line, but it also may be somewhere above where the error truly started to happen, just like when you buttoned your shirt wrong. The first few times that you get an error, you're going to sort of freak out and you'll have no idea what's going on. Don't panic. Take a deep breath, look carefully at the error message, read it completely, figure out whether it's a syntax error or a runtime error, and then look carefully at the line where the error occurred. And again, because of our shirt buttoning problem, you might need to look a little bit above where the error was pointed out if you have a syntax error. After a while, you'll get used to seeing some of these errors come up. And when you see an error, you won't need to freak out. You'll say, oh yeah, I remember that one, and I remember how I fixed it. And your programming will be ever so much faster. Earlier, we talked about expressions of the form variable equal variable plus 1 being very common. In general, updating variables is quite common in Java programs. Presume that the variables in these examples have been declared elsewhere in the program. Whenever you have this pattern, where a variable is updated by an arithmetic operation, you can use an augmented assignment operator. These expressions turn into these simpler expressions. Age plus and becomes 1 is the same as age equals age plus 1. Limit minus and becomes 5 is the same as limit equals limit minus 5, and so on. If you don't have a simple update, then you can't use the augmented assignment. There's no way to use augmented assignment to simplify this expression. Sorry. Let's get back to adding 1 and subtracting 1, also called incrementing and decrementing, which are among the most common operations that programs perform. There's a special shortcut for this: plus plus for increment and minus minus for decrement. This updates the variable without needing an equal sign. The variable is changed in place. You can also put the operator before the variable name, as shown here. Why two versions, and what's the difference? When the operators are all by themselves, as in this example, there's really no difference. But when you put them in an expression with other operations, there's a big difference. Here, the plus plus follows the variable, and it's called a post increment. This is what things look like after we initialize quantity in the first line. Let's see what happens when Java encounters the second statement. It accesses the value of quantity, which is 10. Then the plus plus takes effect, and the variable quantity becomes 11. But our scratch paper still says 10. When we do the multiplication, we get a result of 50 and assign that result to the variable total. Now let's try it with the plus plus before the variable name, which is called a pre-increment. At the end of the first statement, quantity is still 10. And at the beginning of the second statement, we pull out a piece of scratch paper for the right-hand side of the equal sign. Because the plus plus comes before the variable name, the increment happens before we access the value of the variable. Now when we look at quantity, we get 11 and multiply that by 5, getting 55, which goes into our total. I don't recommend writing this sort of thing. I don't think it adds to clarity. However, you will see this in programs that other people write, and you need to know how to interpret it correctly. For example, how would you solve this problem? If you ever see an expression like this, here's a technique that will be very useful for you. Find everything with a pre-operator, the plus plus or minus minus preceding the variable name, and write it out completely before the statement in question. Now find everything with a post operator, the plus plus or minus minus following the variable name, and write it out after the statement. Now go through the statements in order. Here's our situation after the first two statements. We add 1 to y. Then we do the multiplication. And then we subtract 1 from x. Again, I would recommend writing this code as 3 statements rather than the original combination, which I think is much harder to understand. One final word of warning. What happens if you use the same variable with both pre and post operators on the right-hand side of an equal sign? Answer: don't. Just don't. Not only is it hard to understand, but in other programming languages, the result could be completely undefined. In summary, most of the time you will use the increment and decrement operators all by themselves. If you use them in expressions with other operators, you have to be careful to choose whether to put the operator before or after the variable, depending on the effect you want. In the interest of code clarity, you might want to avoid this sort of expression altogether and write things out completely. Up until now, we haven't been able to test for conditions. We do the same instructions every time. The Java if statement lets us do things depending on whether some condition is true or false. Here's the flowchart. And here's the generic form. If some condition is true, we do the statements inside a block. Otherwise, we don't do the statements at all. That's a bit abstract, so let's write a program that asks the user for an integer. If the integer is even, it gives a message that says so. And if the integer is a multiple of 7, the program gives a message saying so. What happens if we enter 18 as our input? The first condition tests to see whether 18 mod 2, the remainder when you divide 18 by 2, equals 0. Notice that we have 2 equal signs here. We use one equal sign to mean assign a value to a variable. We use 2 equal signs to ask a question. True or false, are these 2 things equal? In this case, the answer is true. 18 mod 2 is 0, so the program will print that 18 is even. Java then proceeds to ask another question. Is the number 18 mod 7 equal to 0? In this case, the answer is false, because 18 mod 7 is 4, and 4 is certainly not equal to 0. Because the condition is false, Java does not do the statement in the block and doesn't print that message. And when we run the program and enter 18, we get only the message that 18 is even. What would happen if we gave 21 as an input? Our first condition, is 21 mod 2 equal to 0? No, it isn't, so we won't print out that it's even. In the second condition, is 21 mod 7 equal to 0? Yes, 21 divided by 7 gives you a remainder of 0, so the program will print out that 21 is a multiple of 7. Let's try that and enter 21, and that's the message we get. What if we enter 28 for our number? The first condition will be true. 28 mod 2 equals 0, so the program will tell us that 28 is even. 28 mod 7 is also equal to 0, and the program will tell us that 28 is a multiple of 7. And sure enough, we get both messages. What will happen with 19 as an input? 19 mod 2 is not equal to 0, so we won't get the first message. 19 mod 7 is not equal to 0, so we won't get the second message. In this case, when we enter 19, we'll get no output at all. What you've just seen is a one-way or unary if statement. There's another kind of if statement that's also very common, where you ask a true or false question and do one thing if the answer is true and something different if the answer is false. Here's the generic model in Java. If some condition is true, we do one block of statements. Otherwise, the condition is false, and we do a different block of statements. Let's put that into our age in days program. As it currently stands, if you run the program and enter a negative number or 0, the program will calculate an age even though the input really doesn't make any sense. Let's use an if-else to fix that. Once we get the number of years, we're going to ask if the years is greater than 0. If that's true, then we want to do both of these statements. We'll indent them in the block and put in a closing brace. Now I need to specify what to do if my condition, years greater than 0, is false. That's the else block, and I will print a message that says age must be greater than 0. And again, that block will be inside of braces. Let's compile this and run it. If I say 30 years old, everything works great. If I say -5, I get my error message. And that's how you'd use if and if-else statements in Java. Let's talk about using braces in if statements. When you have exactly one statement after an if or else, you can leave out the braces, as shown on lines 14 and 15 in this program. If I run this program and say I want 10 items, it charges me $80. I don't get a discount. If I say I want 20 items, which is greater than 15, I get my 10% discount. Now let's modify the program to let the user know that they got that 10% discount. This is the additional line that I've added. When I run the program with 20 items, we get the message and the discount. However, if I run the program with 10 items, I don't get a message, but I still get the discount. Why did this happen? Because line 16, even though visually it's indented as if it were part of the if statement, doesn't belong to the if. Remember, without braces, only one statement belongs to the if. Line 15 belongs to the if. As far as Java is concerned, the total really is indented out here. This is not what we want. Instead, we need both statements to be part of the if. So what we need to do is put braces around them to group them together and also indent them properly. Let's recompile. And this time, when I have 20 items, I get the message and the discount. And if I have 10 items, I don't get a message and I don't get the discount either. Another problem with leaving off braces happens when you have nested if statements with one else. What happens if you order 10 items in this program? 10 is not greater than 20, And the way it's written, your eyes tell you that you'll get a 10% discount because the else is lined up with the first if. Let's see what happens. When we say 10, we get the full price. We don't get the discount. Why did this happen? The rule is that an else is always joined to the nearest if. What we really have is this else and this discount belonging to this if, not the if on line 14. If we add braces to group things together, this is what we're really looking at. And that's why with a quantity of 10, we don't get either a 20 or a 10% discount. The book tells you to be careful when writing if statements and to put braces in where they're needed. I say no. The real solution is to always use braces even when there's only one statement, because eventually you're going to want to add some other statement, and at that point you'll need to have the braces. You may as well put them in from the beginning. The ambiguous else problem is always solved by indenting properly and using braces everywhere. Why do we have this no braces with one statement rule anyway? Back in the 1980s, when disk sizes were measured in megabytes, or even kilobytes for personal computers, and CPU speeds were on the microsecond scale, every byte counted, and every extra byte, or brace, that you added slowed down compile speeds and took up more room. In a large program, braces on 500 if statements would add a large burden. Minimizing code size was a worthwhile goal. Now disk space is measured in gigabytes and CPUs run at nanosecond speeds. So saving 100 nanoseconds and 50 bytes at the expense of 10 minutes of your time to debug a program because you forgot braces where you needed them, not even remotely worth it. In summary, when you're writing if-else statements, use braces in all the places. Sometimes you need to test more than one condition at a time. For example, this. A valid score must be greater than or equal to 0 and less than or equal to 100. Here's how you write that in Java. The AND is written with 2 ampersands in a row. For an AND to be true, both conditions must be true. Here's the truth table that shows how AND works. That's a bit abstract, so here's a concrete example. The only combination that works, having both a square and a circle, is when both conditions, having a square and having a circle, are true. Another way to combine conditions is with OR. You want to do something when either one of 2 conditions is true, as in this example. Here's how we write that in Java, using 2 vertical bars in a row to mean OR. On US keyboards, the vertical bar is on the key with the backslash. It may be shown as a broken vertical bar, and that's to distinguish it from the capital letter I. Here's the truth table for OR. And here's an example with the squares and circles. The only part that seems weird to people is this last case. If you have both a square and a circle, you still have at least one of them, so this turns out to be true. What if you really do want either A or B but not both, as in this example? Here we don't want to mail an envelope that's too small, but we don't want to mail one that's too big either. Here's the code for that in Java, using the circumflex for the operation, whose official name is exclusive OR. Here is its truth table. The result is true only when the operands are different. And here's the example with the envelope length and width. Just as with arithmetic operators, where multiplication and division are more important than addition and subtraction, logical operators also have precedence. That means that this test, as written, is wrong. Without parentheses, this says that the discount is for young people on Saturdays or for anyone on Sunday. To make this work correctly, we need to use parentheses to force the OR to be grouped together and done first. Most people don't have the precedence tables memorized, especially for logical operators. Don't leave this to chance. When in doubt, and even if you aren't in doubt, use parentheses to make your intention clear. In Java, you can put if statements inside of if statements, and that's called a nested if. Here's a program that asks for a price and quantity, and calculates the subtotal, the tax, and the total, and prints them out. Let's run it. If I have a unit price of $4.50 and I order 7 items, there's my subtotal, tax, and total. I'd like to be sure that both the price and quantity are greater than 0. Let's add an if-else for the price. After I get the price, I want to ask if the price is greater than 0. If that's the case, it's okay to do all these things. I could indent all the statements by hand, one by one, but my integrated development environment gives me a helping hand. If I highlight all the lines and press Tab, it indents them all for me. And I can close the if block by inserting a closing brace. I'll need an else block, in case the price is not greater than 0, to print out the message that the price must be greater than 0. And I'll put the closing brace on that block as well. Let's recompile. And when I run again, if I enter a price of negative $4.95, the program will immediately tell me that the price must be greater than 0. That handles negative prices. But what happens if I give negative quantities? If I give a valid unit price, a positive number, and a negative quantity, it still goes through with that bad calculation. So I need another if-else to handle that. After I get the quantity, I have to ask if the quantity is greater than 0. If it is, then it's okay to do all of my calculations. And again, I'll press Tab to do the indent and close my block. Otherwise, if the quantity is not greater than 0, I'll print the message that says the quantity must be greater than 0 and close that block. I have an if in lines 19 through 28 inside of another if from lines 15 through 31. That's a nested if. Compile and run the program with a valid unit price and a valid quantity, and everything works nicely. With an invalid price, I get an error right away, and with a valid price and an invalid quantity, I get an error message telling me that my quantity must be greater than 0. The program is now working the way I want it to because I have a nested condition, an if within an if. Is it possible to have an if statement inside the else portion? Yes, it is. Here's another way I could have written the invoice program. In this program, I'm asking for both the price and the quantity before I do any of my if statements. Then I ask, is the price greater than 0 and the quantity greater than 0? If both of them are true, then it's okay to do my calculation and output. Otherwise, either the price is less than or equal to 0, or the quantity is less than or equal to 0. In the else portion, I'm going to nest two one-way if statements. If the price is less than or equal to 0, I give an error message. Then I check to see if the quantity is less than or equal to 0. If that's the case, I give an error message to that effect. There's no else needed for either the if in line 27 or the if in line 30, because the only way I can get there is if the price is less than or equal to 0 or the quantity is less than or equal to 0. If they were both greater than 0, I would have handled it here in lines 20 through 25. Let's run this program with valid input first. I'll have an item price of $4.50 and order 10 of them. Everything works great. If my unit price is negative and my quantity is okay, I'm told that the price must be greater than 0. If my unit price is valid but my quantity is negative, I'm told that the quantity must be greater than 0. And if I enter a negative price and a negative quantity, I'm told that both of them are not valid. There's an important point here. In order to do a good test of my program, I have to test all the combinations of good and bad input to make sure I've covered all the cases. Another thing to notice is the difference between this program and the preceding one. In the first version of the program, as soon as I got an error, I gave the error message. In this program, I wait until I have all the input before I give any of the error messages. Which approach is better? That's a design decision. The takeaway from this video is that it's possible to have an if nested inside of an if, or to have an if nested inside of an else. If the design of the program requires it, you can nest ifs and elses inside of one another as deeply as you need to get the effect you need. Here's the flowchart for what the book calls a multi-way if-else. Depending on the percent of your maximum heart rate, this tells what training zone you're in. Let's try it with 73% of your maximum heart rate. Is 73% less than 60%? No, it isn't. That leads us to another question. Is 73% less than or equal to 70? No, it isn't. Which leads us to this question. Is 73% less than or equal to 80%? Yes, it is. So our training zone is moderate, and we've finished. The flowchart translates into this code. Let's trace through it again. Since 73 is not less than or equal to 60, we follow the else, and then ask if 73 is less than or equal to 70. It isn't, so we follow the corresponding else. We ask if 73 is less than or equal to 80. It is, so we print moderate, and don't do the else. You may be wondering why we didn't write this code with compound conditions like this. Let's follow through again with 73% of the maximum heart rate. Is 73 less than or equal to 60? No, it isn't. Since it isn't less than or equal to 60, it must be greater than 60. When we get here, we don't need to ask that question again. We already know the answer. Now, is 73 less than or equal to 70? No, it isn't. That means when we get here, we know that it must be greater than 70 because it wasn't less than or equal, and we don't have to ask that question either. Similar logic applies for the first condition in the last if, the percent greater than 80.0. When you nest if-else sequences into a multi-way if-else, you can avoid testing unnecessary conditions. There's nothing wrong with indenting and putting braces around this chain of if-else statements, But if we had a couple of more heart rate levels, we'd be marching off the right-hand side of the screen. Remember I said this in a preceding video? Braces in all the places? Now it's time to amend that. Braces in almost all the places. The block that's outlined in red is really one gigantic statement. So I'm going to set aside the rule of always using braces and join the else to the preceding if. The same logic applies here. The red outlined statement is one statement, so the else and if can be joined together. And the same can be done with the last statement, and I end up with this. This is far easier to read as all of the conditions line up nicely. With this if-else shortcut, I can now add more conditions without worrying about indenting too deeply. The only time you can use this shortcut is when an if immediately follows an else. Adding these statements before the else forces us to use braces all the way. By the way, if you ran this code with a 73 for the input as the percent, what output would you see? Try and figure it out, and then type this code into a program, run it, and see what actually happens. Most of the time, when you have an if-else chain, your conditions will be testing the same variable. In this chain, in this multi-way if-else, all of the conditions are testing the variable percent, but there's no law that this has to be the case. As long as the if immediately follows an else, you can have a multi-way if-else that checks different variables, as you see in this sequence, that determines the price of a movie ticket depending on the customer's age as the first condition, the day of week as the second condition, and the hour of the day as the third condition. As a test of your understanding, you might want to write a program with code like this. Try various combinations of age, day, and hour, and see if you can tell what the output will be before you run the program. Here's the beginning of a program that asks for a rating from 1 to 5, and then prints a message according to that rating. We could use a multi-way if-else to print the message. Note that the last else clause handles any rating that doesn't match our desired input. When you're testing a set of integers, instead of using a multi-way if-else, you can use a switch statement. Java evaluates the expression following the switch, in this case the rating, and then goes through the cases from beginning to end until it finds a matching one. Let's say we entered a rating of 3. The first case doesn't match, rating isn't 1. The second case doesn't match, rating isn't 2. The third case does match, and Java executes the statement corresponding to the case. The break statement then takes us out of the switch, and Java proceeds with the next statement after the switch. By the way, the default case is the one that Java uses if none of the preceding cases matches. You always put the default case last, so it doesn't need a break after it. You can have more than one statement as the result of a case, and you don't need to put them in braces because of the way case is structured. It's very important to put a break after each of the other cases. If you don't, Java will fall through to the next case. If you were to enter a rating of 2, this incorrect code would print disagree and then proceed to print neutral before the break took it out of the switch. Some people take advantage of this fall-through behavior. In this code, for example, a rating of 1 will match case 1 and print the word strongly, but not a new line, then fall through and print disagree on a new line and then break out of the switch. Case 1 would therefore print strongly disagree. We also have to reverse case 5 and 4 in order to get strongly agree to print out properly. Isn't that clever? No! This is the exact opposite of clever. This code is difficult to read and update. What if we needed to translate this program into a language where the adverb follows the verb? we'd have to redo everything because our clever approach wouldn't work at all. Don't sacrifice readability for the sake of a couple of fewer lines of code. Take a direct approach that uses switch in the normal manner. Here's a program that determines your rebate based on the average amount of your purchases. It asks for the total amount you've purchased and the number of orders you've made. If the number of orders is greater than 0 and the average purchase per order is greater than or equal to $30, congratulations, we calculate your rebate and tell you what it is. Otherwise, you don't get a rebate. Let's run this program with a total of $500 of purchases over 10 orders. That's $50 per order, and we get a rebate. What happens if we run the program again and this time enter 0 for the number of orders? Why did that work? Why didn't the program crash on this division? To answer this, we need to look at the truth table for AND. When the first condition of an AND is true, we need to look at the second condition to figure out what the result will be. But when the first condition is false, there's no need to look at the second condition. We know that the result must be false. Java compiles your code to take advantage of this. When we ran the program with 10 orders, our first condition, 10 greater than 0, was true. Java had to do the division to find out if the second condition, the average being greater than or equal to 30, was true or not. When we gave 0 orders, 0 is not greater than 0. The first condition came back as false, which meant Java didn't have to evaluate the second condition at all. The division never happened. That's why the program was able to complete successfully. This process of evaluating conditions only when necessary is sometimes referred to as short-circuit evaluation. The OR operator also has short-circuit evaluation. When the first condition is true, it doesn't matter what the second condition is. The answer must be true, and Java does not evaluate the second condition at all. It gets short-circuited. Most of the common mathematical functions belong to Java's math class, which is automatically imported into your Java programs. You don't need to import it. Here are the exponential methods. Log gives you the natural log, or log to the base e. The last item in this table isn't a method, it's a constant. Math.E gives you an approximation to the mathematical constant e. Here are some of the trigonometric methods, plus the constant pi. These methods take their argument in radians, not in degrees. To refresh your memory, degrees go from 0 to 360 and tell you how far you've turned around. Radians tell how far you have walked along the circumference of the unit circle, a circle with radius 1, and radians go from 0 to 2 pi. People who aren't math majors expect to enter values in degrees and see results in degrees. That's why Java provides these methods for converting to radians and converting back to degrees. In addition to the cosine, sine, and tangent, Java also provides the inverse operations, the arccosine, arcsine, and arctangent methods. Here are methods for rounding. Ceiling rounds up to the nearest integer, floor rounds down to the nearest integer. Notice their behavior with negative numbers. Rint rounds to the nearest integer. If a number is exactly between two integers, it rounds to the nearest even integer. Half the time it'll round up, half the time it'll round down, and it'll all average out. The round method returns a long when you give it a double. That means you can't do this. Instead, you have to do a cast to make sure you get an integer. We have these methods to find the minimum and maximum of two numbers, and also an absolute value method. Finally, there's the random method, which gives you a random double from 0 up to but not including 1. Here's the generic formula for creating a random number in a given range. And here's how you might use it in a program to generate a random age between 18 up to but not including 66, which would be 18 through 65. As we learned in the first chapter, computers use binary digits, numbers at the hardware level. If all we have is numbers, how do we represent characters, letters and symbols, in numeric form? We use encoding. Remember in grade school when you had a simple code for passing secret messages where A became 1, B became 2, C became 3, and so on? That's the idea. We set up a numeric correspondence for each character. The grade school approach is the right concept, but it's too simplistic for our needs. One standard encoding for characters that includes upper and lowercase numerals and punctuation marks is ASCII, the American Standard Code for Information Interchange. It uses 1 byte per character, which limits it to 256 different encodings. In ASCII, the capital A is encoded as 65, lowercase a as 97, an exclamation point has the numeric value 33, and the numeral 5 has the value 53. ASCII is great, but 256 numbers aren't enough to encode languages other than English, and definitely not enough to encode all of the Korean syllabary or the Japanese and Chinese characters. You need at least 2 bytes for those. In the past, each country came up with its own standard for encoding, and it was pretty much of a mess. Computer manufacturers and computer scientists got together to develop a single encoding to handle all the world's languages, Unicode. That is the system that Java uses for encoding characters as numeric values. In the book, you may have seen code like this. What are those letter and number combinations? Those are base 16 numbers, which are called hexadecimal. What's base 16? Let's take a trip back in time to grade school, where we learned about numbers with the hundreds, tens, and ones columns. 357 meant 3 times 100 plus 5 times 10 plus 7 times 1, which adds up to 357. When we got to algebra, we relabeled the column with powers of 10. which made a good analogy to powers of 2 for the binary system, base 2. In binary, the number 101 is 1 times 2 to the second plus 0 times 2 to the first plus 1 times 2 to the 0, which adds up to 5. I think you know where we're going with this, to the powers of 16. But there's something we have to consider first. In binary, we have 2 numerals, and once they're used up, we go to the next column, the next power of 2. In decimal, we have 10 numerals, and once they're used up, we go to the next column, the next power of 10. For base 16, we'll need 16 numerals. Rather than invent symbols for those extra numerals, we use the letters A through F, which represent 10 through 15 in decimal. That means a hexadecimal number like 13B is what we, in decimal, would call 1 times 16 squared, 256, plus 3 times 16 to the first, 3 times 16, plus B, which corresponds to 11, times 1. And that adds up to 315 in decimal. By the way, you read hexadecimal numbers as a series of individual digits, and we usually abbreviate hexadecimal as hex. The first number here is hex 13C, not 130C. The second number is hex 724, not hex 724. In Java, you can put the hex letters in either upper or lower case. What's so special about 16? Why do we use that as a number base? If you have 4 binary digits, there are 16 possible combinations, each one of which corresponds to a hexadecimal digit. That means 1 byte can be expressed as 2 hex digits and a 16-bit Unicode character as 4 hexadecimal digits. The Unicode charts are organized in columns of 16 rows, and the code points, the numeric equivalents, are shown in hexadecimal. You always use hexadecimal notation when specifying a Unicode character literal or in a string. Remember to precede the hexadecimal with \u. You use hexadecimal for integers on those occasions when you need to express numbers in a form that is closer to the bit patterns. You precede the hexadecimal digits with 0x to indicate that this is a hexadecimal number. Java has the character data type, abbreviated as char. It's expressed as a character in single quotes or a Unicode character in single quotes. Characters also happen to be 16-bit integers, so we could say this, though it is not recommended. If you want to determine whether a character is uppercase, lowercase, or a digit, you can write code like this, where you compare the character value to a range between lowercase a and lowercase z, uppercase a and uppercase z, and the characters 0 through 9. This won't work correctly with Unicode because the numeric values of C cedilla, tilde-n, and the Arabic numeral 3 aren't in the ranges for the encoding of A through Z, capital A through Z, or 0 through 9. Instead, use these methods from the character class, which take Unicode into account and will classify the characters properly. Strings, which consist of more than one character, must be enclosed in double quotes. Notice that the data type is a capital S string because string is a Java class, it's an object. A backslash in a string allows you to enter what's called an escape sequence, such as the new line, \n, or if you can't type Unicode characters directly from your keyboard, Unicode sequences such as \u00e7, which is the C cedilla. You can also use \double quotes to put a double quote inside of a double quoted string, or to put an apostrophe into a single character variable. Unlike the methods that work on characters, which look like this, with the name of the class character and the character you wish to transform is the parameter. Strings are objects. Read from right to left, the second line says, call the toUpperCase method on the message string and assign that value to the variable capitalized. There's a special string called the empty string, which is an opening quote and a closing quote with nothing in between them, not even the space bar. Think of the empty string as the zero of the string universe. We'll see it often in a lot of the examples. Let's go to the shell to demonstrate some of the string methods. Let's create a string message which will get the value of the string welcome to Java. You can convert a string to all uppercase by calling the toUpperCase method on the string, or convert it all to lowercase. Sometimes you have a string with leading and trailing whitespace. For example, username equals, let's put some spaces, a tab, the name, a new line, and a couple of more spaces. Let's see what this looks like if we print it out. And to see where the white space is, we're going to precede it with a vertical bar and follow it with a vertical bar. And you can see that there's leading and trailing white space. The trim method gets rid of this leading and trailing white space. When I say username becomes username.trim, the leading and trailing white space is gone. White space that was within the string and not at the ends stays as it is. When comparing integers or doubles, we use these symbols for doing the comparison. But we can't use those symbols with strings because strings are objects. Instead, we have to use methods in the string class to compare strings. To compare strings for equality, use the equals method. In this example, the string word1 is assigned Java. Asking if word1.equals Java returns true. Word1.equals Python returns false. By the way, when you're doing simple testing, you can use strings directly. You can say java.equals Java, which is true, or python.equals Java, which returns false. Equality really means character for character equal. If the cases are different, the strings are different. If you want to compare strings for equality while ignoring upper and lower case differences, there's a method for that. Equals ignore case. That takes care of equality. What about comparing for less than and greater than? For that, we need the compare to method, which returns a negative number, 0, or positive, depending on how the strings are related to one another. Here's a program that lets us see how it works. We read the first string on line 16, and on line 17 we trim off the leading and trailing whitespace. On line 20 we read the string and trim the whitespace all in one step. This works because input.nextLine returns a string, which becomes the input to trim in the next step. The official name for this trick is chaining methods, passing the output of one method to the input of the next one. Okay, back to business. Lines 22 through 28 do the comparison and give us the appropriate output. If string 1 compared to string 2 gives a number less than 0, that means string 1 is less than string 2. Otherwise, if string 1 compared to string 2 gives a number greater than 0, that means string 1 is greater than string 2. And if it's not less than or greater than 0, it must be equal to 0, which means that the two strings are identical. Let's run the program a few times. When the first string is ant and the second is b, ant is less than b. If we compare zebra to horse, zebra is greater than horse. Comparing anteater to ant says anteater is greater than ant. So far so good. Now let's try this comparison. Cat and compare it to capital D, dog. The result says that cat is greater than dog. Why is that? Remember that the characters in the string have numeric values. The value of lowercase c is 99, and the value for capital D is 68. 99 is greater than 68, so Java says that cat with a lowercase c is greater than dog with a capital D. Just as equals has equals ignore case, Java also provides a compare to ignore case method. This allows you to compare two strings while ignoring their upper and lower case differences. And that's how you compare strings in Java. In many programs, you'll need to extract portions of a string or find out whether strings are contained in other strings. Let's look at portions of a string called substrings first. We extract these substrings using the substring method. When you give the substring method one number, the result is the section from that position to the end of the string. If you give two numbers, you get the section starting at the start index up to but not including the end position. Here's a specific example, the word flashpoint with its character indices numbered. Word.substring5 gets the segment of the string starting at index number 5 all the way to the end. Word.substring2, 5 starts at position 2 up to but not including position 5, which gives you the word ash. To find out if a character or a string is contained within another string, you use the indexOf method. If the character or string is found, it returns the index number where it starts. If not found, it returns -1. Here's an example. In the string pre-reading, the dash is at index 3, and the string re starts at index position 1. The character x is not in the string, and neither is the word real, so these both return -1. Ordinarily, indexOf starts looking at the beginning of the string. You can tell indexOf where to start looking by giving it a starting index position. In this example, the first n at or after position 3 is the n at index number 4. Starting at index 2, the string an is found starting at position 3. If we try finding the letter n starting at index 5, there is none, and there's no an after index 4 in the word. You can tell Java to start looking backwards from the end of the word by using the last indexOf method. In this example, we try to find the first dash looking backwards from the end of the string. It's at position 7. Similarly, the first at looking backwards from the end of the string starts at index 9. If we look backwards for a dash starting at index 5, it's found at index 3. And if we look backwards for at starting at index 8, we'll find it at index 5. And here's an example where it's not found if we try to find a dash looking backwards from position 2. Okay, let's put this all together. We'll ask the person at the keyboard to enter up to 3 words separated by commas, and we'll split them up. There are easier methods to do this, but I want a nice example program. Here's the plan. Look for the first comma using index of and remember its position. Take the substring starting at the beginning and save it. Now, starting one position past the place where we found the comma, search for another comma. Take that substring as our second word, after terming blanks. Starting one space after the second comma, we take the substring to the end of the input, and that's our third word. Let's look at a program that implements this. Instead of trying to do the whole program at once, we'll build it up in parts. In lines 11 and 12, we prompt for and read a phrase from the user. In lines 14 through 16, we initialize our 3 words to the empty string. On line 18, we find the first comma in the phrase by using index of. If there is a comma, that index will be greater than or equal to 0, and we use the substring method starting at the beginning of the phrase up to the first comma, but not including it, and that's assigned to word 1. If the first comma is negative, that means there wasn't a comma anywhere, and the whole phrase becomes our first word. There are no second and third words. We'll then trim leading and trailing spaces from all our words and display them. Let's compile that and run it and try it with 3 words, bee, horse, toucan, and it found the first word correctly. Now that we know that this works, we can add the remainder of the program. We need to find the position of the second comma. That becomes the index of a comma in the phrase, starting where we found the first comma plus 1 place past the first comma. If we found one, second comma will be greater than or equal to 0. We'll extract the second word. It'll become the phrase substring, starting 1 place past the first comma, up to but not including the place where we found our second comma. The third word will become the substring of the phrase, starting 1 past the second comma to the end of the word. If we didn't have a second comma, the second word becomes the substring of the phrase, starting 1 past the first comma to the end. Let's recompile and let's run it. First with 1 word, then with 2 words, and finally with 3 words. And that's how you can use index of and substring together to let you find and split up strings. Here's a flowchart of a while loop. It starts by testing a condition. If the condition is true, we do the loop body, and then we loop back to test the condition again. As long as it's true, we continue to do the loop body and go back to test the condition again. When the condition becomes false, the loop is concluded. Here's how we write this while loop in Java. And here's an example of a program that uses a while. We want to find the value of n for which the sum of squares up to and including n is greater than or equal to 100. Here's the flowchart. We start by setting n and the sum of squares to 0. If the sum of squares is less than 100, we have to add 1 to n, add n squared to the sum, and then, to see how the loop is progressing, we print them. We loop back to the condition. Eventually, the sum of squares will not be less than 100. We will have achieved our goal, and we can print the answer. Here's the Java program. In lines 12 and 13, we initialize our variables. Line 15 begins the while, where we test the condition. The parentheses around the condition are required. By convention, the word while is followed by a space. At the moment, the sum of squares is 0. The condition 0 less than 100 is true, so we do the loop body. N becomes 1. 0 plus 1 times 1 is 1, which becomes our new sum of squares. And to show that the loop is proceeding, we print them out. Java loops back to the condition. 1 less than 100 is true. We do the loop body again, and N becomes 2. 1 plus 2 times 2 is 5, the new sum of squares. We print them, and loop back to the condition yet again. This process continues as long as the sum of squares is less than 100. At some point, the condition will be false. The sum of squares will be greater than or equal to 100. The while loop will conclude, and Java continues on lines 21 and 22 to print the answer properly labeled. Let's give ourselves some room to see this in action and run the program. There's the output from inside the loop, and there's the answer that we got after the loop was concluded. And that is a while loop in Java. Here's the flowchart for a program that asks the user for a year and tells them whether it's a leap year or not. Here's the code. There's nothing wrong with it, except that when we test the program, it only does 1 year at a time. If we want to test another year, we have to run the program again and again. What we'd really like is to run the program once and have it ask us over and over again for years. This is a perfect use for a while loop. Here's a revised flowchart. We'll ask for a year and then test a condition. As long as the condition is true, we process the year, ask for the next year, and loop back to see if we should continue or not. The question now becomes, what's a good condition to test? We need some value for the year that will tell the program, okay, I'm finished. This value is called a sentinel value. It's a special value that doesn't represent valid data, but instead tells the while loop that it's time to stop. In this case, our sentinel value is 0. This is an ideal sentinel. There's no year 0, so we can use that as our special, okay, we've finished value. That means we continue the loop as long as the year is not 0. Let's update our code. First, we'll change the description of the program to add that we do this until the user gives us 0 for the year. We'll change our prompt to reflect that. Enter a year, or 0 says quit. After we get the year, we'll add our while with the condition year not equal to 0 and an opening brace. The test for leap year becomes the body of our loop. We indent it and put a closing brace to close our while loop. After we process 1 year, we have to add code to ask for the next year. We'll print our prompt, enter another year, or 0 to quit, and we'll get the user's next input. Let's compile that, and let's run it. This time, when I enter a year, It asks me for another one, and another one, and another one. Until I'm ready to stop, I enter 0, and the program ends. And that's how you can use a loop to repeatedly ask for input. In the preceding video, we had to ask for input twice, once before entering the loop, and then at the bottom of the loop to get the next number. Here it is in the code where we do input outside the loop and inside the loop at the bottom. Depending on your philosophy of programming, this is inelegant because it duplicates code. We'd like to do the input only once inside the loop. Here's the pseudocode. The key is to set a Boolean that tells us whether we have finished or not. The initial value is false because we're just starting, so we're certainly not finished yet. As long as we're not finished, we ask for the year. Say the user enters 2023. 2023 is not 0, so we determine whether it's a leap year or not. It isn't, and print the result. We then loop back to our condition. Finished is still false, which means not finished is true, and we have to do the loop body again. We ask for the year again, and this time let's have the user enter 0. Now our condition is false. 0 is equal to 0. We set finished to true and loop back to test the condition. The condition evaluates as not true, which is false, and that ends the loop. We'll add the variables for the year and the Boolean finished, which starts off as false. We'll put in the while with the condition not finished, indent the loop body, and put in the closing curly brace for the while. Since we've already declared year in line 14, we don't need to declare it again in line 20. After we get the input, we need to check if year is equal to 0 or not. If the year is not 0, then the body of the if gets indented. We do the leap year test. Otherwise, we set finished to true. When the user enters 0, we've finished the loop. Let's compile and run it, and we can enter years to our heart's content until we enter 0 to finish the program. Using a Boolean to control the loop lets us write a program that needs to ask for input only once. In the preceding videos, the reason we had to do input before the loop and at the bottom, or set a Boolean to tell whether the loop is done, is because the while loop checks for the condition before it does the loop body. If the initial test of the condition comes back false, the loop body never happens at all. But we need to ask for input at least once. To handle the case when you want to go through a loop at least once, Java provides the do-while loop, whose flowchart looks like this. The loop body happens first, and then the condition gets tested. You are guaranteed at least one trip through the loop. Here's how you write it in Java. You must follow the condition with a semicolon to end the do-while statement. And here's the code for our leap year test program using do-while. We start with do, and in the body of the loop, we'll prompt for input. If it's not 0, we'll check to see if it's a leap year or not, and print the result. We do all of this as long as the year is not equal to 0. Let's compile and run it and see that it works exactly the same as the others. In summary, while tests the condition first. If it's false, the loop body won't be executed at all. Do while tests the condition last. The loop body will be executed at least once. Here's the flowchart for an ordinary while loop. Sometimes you want to break out of a loop before the condition becomes false. You use a break statement to do that. Here's an example of a program that finds the smallest factor of an integer. I've highlighted the while loop with its break statement. Let's take a closer look at how this while loop works. Presuming that the user has entered 21 as their number, we start factor as 2. Our while condition tests if 2 is less than or equal to 21. It is, and that means we enter the loop. We then check to see if 21 is divisible by 2. It isn't, so we increment factor. We come back to the condition. 3 is less than or equal to 21. 21 is divisible by 3. That ends our loop. And the correct answer is that the smallest factor of 21 is 3. Some people don't like to use break as it provides a second exit point from our loop. The first exit point is the condition, the second one being the break. If I see something like this in your programs with while true, I get very suspicious that you haven't thought through your conditions. There are two ways to get around needing break. One is to set a Boolean flag, as we have in this program. On line 18, I set a Boolean named found to false. Our loop condition changes. While we haven't reached n as a factor, and we still haven't found the smallest factor, we test to see if n mod factor equals 0, if it's divisible. If so, we set found to true. Otherwise, we go on to the next factor. At some point, we will find something that's divisible, found will be true, and this compound condition will come out to false, and will exit the loop from the condition. The book says that this is much less readable than break. However, we can go one step further and eliminate both the break and our Boolean flag. In this version of the program, we put our test for divisibility into the while loop condition. As long as the factor is less than or equal to n, and it doesn't divide it evenly, we move on to the next number. Pulling the break condition into the while condition takes extra thought and planning, but it's well worth it. The other concept that I want to touch on very briefly is continue. Continue jumps to the end of the loop and starts the next iteration. It doesn't exit the loop. This is not as commonly used as break. You can almost always use an if statement to get the same effect. Here's a program that uses continue. The program counts from 1 up to 10, skipping over 7 and 8. Let's run the program, and you'll see that it does exactly that. In summary, though you will very seldom need a continue to skip over part of a loop iteration, you'll more often see break used to provide an extra exit from a loop, though you should use it carefully and only when absolutely necessary. Let's consider a function definition in algebra. You can think of a function as a black box that takes some input and provides some output. The x in our function definition is a parameter. When we apply the function, in this case by calculating f of 1.5, 1.5 is the argument of the function. It's the input to our black box. The result of applying the function, the output from the black box, can be assigned to a different algebraic variable, in this case y. The Java term for a function is a method. How do we make an equivalent method in Java? First, we start off with a modifier. For now, we will always be using public static. More on that later in the course. We then give the name of the method and our parameter name. Here's where we part company with the world of algebra. In algebra, we just sort of know that the domain and range of f is the real numbers. In Java, we must specify the type of the parameter and also the type of the value that the method returns. In the body of the method, we calculate the result and use the return statement to send back the result. In algebra, you apply a function. In Java, we call a method. Here's an example of a method call. On the right-hand side, the argument 1.5 is copied into the parameter x. It's used in the calculation, and the result gets returned. And that becomes the value of the right-hand side, which is then assigned to y. Let's write a program to solve this problem. Which combination of quantity, price, and discount is cheaper? Here's the code with the method named getTotal to calculate the total price, and a main method that calls getTotal. What really happens when we call methods in Java? We start in the main method, and Java allocates memory for variable amount1. Every time Java starts a method, it creates a stack activation record that keeps track of the method's variables. Java then has to evaluate the right-hand side of the equal sign. This requires a call to getTotal. That call creates a new activation record that gets stacked on top of the record for main, sort of like a stack of building blocks. GetTotal allocates space for the three parameters, and the three arguments, 12, 3.5, and 7.5, get copied into those parameters. We then calculate the total, and then get to the return statement, which does two things. It takes the method's activation record off the stack and sends the return value back to the method that made the call. Now that we have the value of the right-hand side, we can assign it to amount1. Continuing on in main, we allocate room for variable amount2, and on the right-hand side there's another call to getTotal. Java once again creates an activation record for getTotal and stacks it on top of mains. It allocates room for the parameters and copies the argument values 14, 3.05, and 9.25 into the parameters. We again calculate the total using these different numbers and get to return, which removes getTotal's activation record from the stack and sends the total of 38.75 back to the caller, where it gets assigned to amount2. And that's what happens behind the scenes in a Java method call. Java lets you define multiple methods with the same name. This is called overloading a method. Here's a method that returns the maximum of two integers. I can call the method using two integers, but if I make a call using two doubles and try to compile it, I get an error. The solution is to create a new method that returns a double that has the same name, as long as the parameter list has either a different number of parameters or different types for those parameters. Java will let me do this. The code inside the method will be exactly the same. Now, when I compile the program, it succeeds. When I make this call with two integers, Java will select this version of the max method to call. When I make this call with two doubles, Java will call this version of the method. What happens if I try this? 3, which is an integer, and 4.7, which is a double. Which one gets called then? The answer is Java figures out which is the best match. The best match is this one, and the reason is because the integer 3 can be promoted to a double, whereas the 4.7 cannot automatically be converted to an integer. I can even overload to have more parameters. I can have an integer returning method called max that takes 3 integers, a, b, and c. In this case, the algorithm says take the maximum of a and b and then return the maximum of that value and c. Again, when Java sees this call, it'll find the best match. Since a and b are integers, it'll call this method. And the same will happen here. And I can write a line to test that, the maximum of 7, 10, and 3. Let's compile it. The moral of the story: you can overload a method. You can provide multiple versions as long as the parameter lists have different lengths or different data types. Here's part of a program that takes a week's worth of temperatures in degrees Celsius, calculates the average, and then determines how many of them are above average and how many are at or below average. I've already typed the part that defines 7 variables, temperature 1 through temperature 7. Now I'll add them up. And calculate the average. Then, to calculate the number of items above the average, I'll set n above to 0, and then do this. If temperature 1 is greater than the average, add 1 to n above. Similarly, I can say if temperature 2 greater than average, n above is incremented, and then I'll copy and paste it. 1, 2, and make the changes for temperature 3, temperature 4, 5, 6, and 7. And now let's put in some code to display the output. the average temperature for the number of days Celsius \n, 7 days, and our average. And the number of days above average, which is n above, and the number of days at or below the average, 7 minus the number above. Let's save this and compile it, and then let's run it. There's the average temperature, 22.8 degrees Celsius, 3 were above and 4 were below average. This program works, but what if we had a whole month's worth of temperatures? Then we'd have to have 30 repetitions of this if statement. We'd have to have 30 additions, and oh boy, it would be a tremendous mess. There must be a better way. Let's think back to algebra, where we had a variable name with a subscript to represent a group of related values. And then we could use that subscripted variable in a summation expression. Now let's think about Java. Remember that we've treated variables like named mailboxes, and each person has their own named mailbox. But if you go to an apartment building, you'll see one name, and each mailbox will have an apartment number on it. We have a group of mailboxes all associated with one name. In a similar way, in Java, individual variables are like individual mailboxes. The equivalent of the apartment building mailbox group is an array. We use the square brackets after the data type to indicate that this is an array, and we can initialize the entries by listing them in braces. Unlike apartment numbers, which begin at 1, the positions in an array start numbering at 0. And unlike algebra, where we use subscripts, we can't type subscripts in our editor, so we use square brackets to indicate the index, or the mailbox number, that we're accessing. With this knowledge, let's modify the program. First, I'm going to initialize the array with an alternate method. I'm going to declare the array as a double array named temperatures, and it will be a new double array of length 7. I don't need the word double on any of these anymore. And I'm going to change them to individually set each element of the array, starting at element 0, element 1, all the way up to 6. Now, instead of adding up all of the items in one expression, I'm going to do something that looks really weird. I'm going to set an index equal to 0, and I'm going to set my sum equal to 0. Then I'm going to set sum to sum plus temperatures at location index. That will be slot number 0, which will take 0 plus 27.2. Sum will be 27.2 when I'm done with this statement. I'll then add 1 to index to increment it. Now I'm going to do exactly the same thing again. This time index is 1, which means it'll take the 27.2 and add temperatures sub 1, which is 20, and sum will become 47.2. Then I'll do index plus plus. you're probably thinking, oh no, this is even worse than the original version. Is he actually going to copy and paste this 5 more times? No, I won't. When I see myself doing the same thing repetitively, I think, hey, can I do this with the loop? The answer is yes, I can. I'm going to say for index equals 0, index less than 7, index plus plus, sum becomes sum plus temperatures of index. And that is the same as if I had written this 7 times. In the interest of good programming style, I'm going to make this int index, and then I don't need this line anymore. And now, my average is the sum divided by 7. This works great, but if I ever decide to do 14 days or 30 days of temperatures, I'd have to change this 7 to 14 or 30, and then I'd have to change this one and this one. When I initialize the array, I have to know how long it's going to be. For this one, instead of saying 7, I can say the number of items that are in the array. That's temperatures.length. If I have 14 items, this will turn out to be 14. If I have 30 items, it'll be 30. Same thing here. I'm going to divide by the number of items in the array. Now I can do a similar loop to find the number of temperatures that are above average. I can say the number above is 0, and then for int index equals 0, index less than temperatures dot length, index plus plus. If the temperatures at my current index is greater than the average, then the number above gets incremented. Let's do the output. The average temperature for days. And this time again, instead of 7, I'm going to say temperatures.length and average. I can say number of days above average, and that's going to be n above, and the number of days at or below average is temperatures.length minus the number above. Let's compile that, and let's run it. And you'll see that it does exactly the same as the other one, except the program is a lot shorter. Again, because I'm using temperatures.length everywhere, if I have more temperatures, my program is still going to work. Let me change to the brace initialization method and set the first 7 to the way they are here, and add a few more temperatures. Let's go up to 32.3, 31.8, 31.7, 30.0, 29.5, 29.5, and 29.3. I won't need these anymore. And everything else in my program is going to be exactly the same as it was before. Let's compile it. And let's run it. And this time it gives me the average temperature for 14 days and calculates the number above and below. Arrays and for loops are a marriage made in heaven for dealing with multiple related values of data. Let's review what happens when you assign variables. If we set a to 22, an area of memory is assigned to that variable. When we say int b becomes a new area of memory is assigned to variable b, and the value in a is copied into that area. Arrays are different. When you create a new array, as shown here, memory gets allocated for the array elements. What goes into the memory location associated with the variable a is a reference to where to find those elements. Arrays, like objects, which we will learn about later, are reference types. This has implications for assigning arrays. When we do an assignment like this, array B equals array A, the reference is copied to array B. Both of them are referring to the same area of memory. That means when I set array B sub 1 to 999, and then print array A sub 1, it will also be 999. Here's the code in Java. Let's run it to show you that that's what's really happening. And sure enough, it prints 999. So, given this, how do we really make a new copy of an array, rather than two references to the same area of memory? Here are two methods. The first is to create a brand new array. This is a reference to a completely separate area of memory, initialized to zeros. Then run a loop for the length of the original array to copy the contents. Now, changing one array's contents doesn't affect the other array at all, because they're in two separate areas of memory. Another method is to create a brand new array, and we'll make one that is the same length as A by saying array A.length, and then use the system.arrayCopy method. The system.arrayCopy method has these parameters: the source array, the array that we're copying from, the starting index in that array, the destination array, the one we're copying to, the starting index in the destination, and the number of items to copy. Now, if I set array C sub 2 to 777, and I print array A sub 2, it will be different than the contents of array C sub 2. Let's clear our terminal and run it again, and sure enough, we have two different arrays. The important point to remember is that arrays are reference types. This will be important when we discuss objects, and also when we investigate passing arrays as arguments to methods. Let's look at this program that uses printf. There's something interesting here. The first call has 2 arguments, the second call has 3 arguments, and the last call has 4 arguments. But in all the methods we've written so far, we've had to specify exactly how many arguments a method can have. What strange sorcery is this that allows you to give printf as many arguments as you'd like? The answer is that Java lets you specify that a method can have a variable number of arguments. We're going to write a method that returns the maximum of any number of arguments, so that we can write a program like this, printing the maximum of 2 integers, the maximum of 3 integers, or the maximum of a whole group of integers. Here's the method header. It's going to return an int. We'll call it max, and the parameter will be int ... numbers. The 3 dots tell Java to expect a variable number of arguments and to treat them as if they were an array. The body of the method looks like this. We'll set our maximum value to be the first argument, which is the first element of the argument array in this case. And then we'll iterate through the remaining numbers. If one of the arguments is greater than the current maximum, it becomes the current maximum. When we're out of the loop, we'll return that maximum. Let's compile that. And let's run it. And it works. Because the variable arguments are treated as an array, you can also pass an array to this method. I can create an integer array called data, which has some numbers in it. And then I can use the array as an argument. Compile and run, and that works too. There are two restrictions on using variable arguments. You can't have more than one variable arguments parameter, and the variable arguments parameter must be the last one in the parameter list. One of the things we commonly do in programming is find where an item is within an array. Consider this array of integers. We'd like to find out where the number 15 is in the array. The way we do it by hand is to scan the array from left to right until we find the number, as in this case, or if we get to the end and we haven't found the number. Let's write the code to do a linear search through a data array, looking for a given value and returning the position where it was found. We'll run a for loop starting at the beginning of the array, as long as the position is less than the length of the array, one position at a time. And if the data at the position that we're looking at equals the value we're looking for, we'll return that position. If we get out of the loop without returning anything, that means the value wasn't in the array, and we'll return -1 to indicate an invalid index. Here's our main program. It sets up an array of integers and then has a do-while loop that asks for a number to find, a value, does a linear search through the data array and tells where it was found, and prints the result. Let's compile that. And let's run it. We'll look for 15. It's at index 3. Let's look for 78, which isn't in the array, and it gives us back a -1. When testing a program, you want to test at the boundaries. You want to test to see that it will find the first element in the array and the last element in the array. And this program works. That's our linear search. Although the program works, my personal preference is to have only one return from a method than having two different places where we return a value. Let's rewrite this method to use only one return. The way we're going to do this is we're going to start our position at 0. As long as there are items left to look at in the data array, and the one that we're currently looking at is not equal to the value, we move on to the next position. Once we exit the loop, we're going to see if the position is less than the length of the array. If so, that's where it was found. Otherwise, it's not found. and we'll use the ternary operator instead of an if statement. We're going to return if the position is less than data.length, the position, otherwise -1. Let's compile that, and let's run it. 15 is found at index 3, 78 isn't in the array, 37 is at the beginning, and 56 is at the end. And this algorithm also works. One thing to note, the time required for this algorithm is proportional to the number of items. If your array has 60 items, then on the average it will take 10 times as long as when the array has only 6 items. In our next video, we'll examine a more efficient search, the binary search. Consider this array with a list of 2-letter country codes. They're already in alphabetical, sorted order. Let's say we want to find ES, the country code for Spain. We can use the fact that the array is sorted to our advantage. We'll set an index to the low and high elements of the array and mid to the middle element using integer division by 2. ES comes alphabetically before HU, and because the array is in order, that means we don't have to look at HU or anything that comes after it. Instead, we'll set the high marker to 1 less than the middle index and recalculate the middle point. ES comes after DE, so we set the low marker to 1 past the middle, eliminating Austria, Australia, and Germany, and recalculate the middle point. We found Spain, and we return its index, 3. What if we'd been looking for Fiji, FJ? In that case, since FJ is bigger than ES, we'd recalculate, and now our low and high indices would meet. FJ is less than the middle element, which means we set the high element to the middle -1, at which point the high and low have switched places. Whenever that happens, that means the item isn't in the array. It so happens that at this point the low index shows where the item would go if it were to be inserted in the array. Now let's write the program that implements this algorithm. Here's our main method. It defines the array of countries, and then in a do-while loop, it prompts for a country code, reads it in, converts it to uppercase, and does a binary search through the countries array to find the given value. Inside binary search, we'll have an integer, low, set to 0, and high set to data.length -1, the last element. As long as the high index is greater than or equal to the low index, we'll set the middle element to high plus low divided by 2. If the data at the middle index equals the value we're looking for, we'll return the middle index. Otherwise, if the value compared to the middle index is less than 0, which means the value is less than the middle point, we'll set the high point to mid -1. Otherwise, since it's not equal or less than, it must be greater than, and we'll set the low point to mid +1. That ends our loop. The question now comes, what should we return when we get out of the loop if something's not found? We could return -1, but since low tells us where the not found value should go, why not return -low? That looks good until you realize what happens when something belongs at position 0. It would return -0, and -0 is indistinguishable from 0. The answer is, let's take negative low and subtract 1. That way something that belonged at position 0, which wasn't in the array, would give us a negative 1. Let's compile this, and let's run it. We'll search for ES, found at index 3. And again, let's test with the beginning element and the ending element and one that isn't in the array at all. And there's our working binary search method. How does this search perform compared to linear search? Really well. Let's say we have 1,000 items all in order. Our first test eliminates 500 items from consideration. The next will eliminate 250, then 125, and so on. It will take a maximum of 10 comparisons to find any item in a list of length 1000. The performance of binary search is proportional to log to the base 2 of n, but it only works when your data is in sorted order already. Consider this table of quarterly sales over 3 years. It's a two-dimensional table with rows and columns. Here's how we represent it in Java. We use 2 sets of square brackets instead of 1, and we put each row of the table in its own set of braces. You might be thinking, that looks a lot like an array that has 3 arrays in it, and you'd be entirely correct. Here's what's happening behind the scenes. Sales is a reference to an array of length 3, as there are 3 rows, and each item in that array is a reference to another array that has the elements for that row. That means that if we ask for the length of the sales array, we'll get 3. Let's go to a Java program and try it. We'll do system.out.println length of sales is plus sales.length. Compile it and run it, and the length of the sales is 3. If we want to find out how many columns the array has, we look at the length of one of its rows. Let's find the number of columns in row 0 is sales sub 0, which is the first subarray, and its length. And let's run it. And the number of columns in row 0 is 4. In this array, all our rows have the same number of elements. But because of the way Java stores 2D arrays, there's no law that says that rows must have equal length. To access an individual element of an array, you need to use 2 sets of square brackets with the row number first, then the column number. Sales sub 02 is row 0, column 2, and sales sub 21 is row 2, column 1. Now let's write code to get the grand total of the numbers in the array. We'll set our grand total to 0, and then I'll need a nested loop. The outer loop will iterate through the rows. For int row equals 0, row less than sales.length, row plus plus. Notice that I am using row as my counter variable rather than I. This makes the code much more understandable. My inner loop will iterate over the columns. For column equals 0, column less than sales sub row dot length. Remember, the number of items in each subarray is the number of columns. And then we'll add 1 to the number of columns. And inside this nested loop, we'll set the grand total to be the previous value plus the item at the given row and column. Once we're out of the loop, we print the grand total properly labeled. And I'll use printf for that. The grand total is done. And with 0.2f, so it looks like a monetary format. And grand total. Let's recompile and rerun it. And the grand total is 186. Now let's get the yearly totals. We'll set a constant base year to be our first year, 2016. And in this loop, we're going to iterate over the rows because each row represents a year. And at this point, we set our yearly total to 0. Unlike the grand total, we have to set the yearly total to 0 at the beginning of each year. Then we can run our column loop. For column equals 0, column less than sales sub row dot length, column plus plus, our yearly total will be incremented by the sales for the given row and column. After we've processed a row, we print its results. Total for the year is, and the year will be the base year plus the row, and the yearly total. The print on lines 27 and 28 is inside the row loop. We need to print this after we process each row. Let's compile. And let's run. And there are our yearly totals. Finally, we'll have another nested loop to print our quarterly results. This time the outer loop will iterate over the column because each column represents a quarter. For int column equals 0, column less than sales sub 0 dot length, and I'm using row 0 here because all of my rows happen to be the same length. In this case, I'm going to set my quarterly total to 0 at the beginning of each column, and then I'll go down the rows for that column. And my quarterly total plus n becomes sales row column. It's important to note that when you access the array element, you always put the row first. Even though your outer loop may be going over the columns first, you always access an element in the array by its row and then its column. At the end of processing each column, we print the quarterly result. The total for quarter is, we'll fill in the column plus 1. Remember, our column goes 0, 1, 2, 3, but humans expect to see Q1, Q2, Q3, and Q4, and our quarterly total. Let's save that and compile. And run. And that's what you need to know to work with multidimensional arrays. Here's a table where we've asked people to choose their favorite pairs of colors from these choices. The order of the colors doesn't matter, so we need to fill in only half the table. Red and blue is the same combination as blue and red. We can represent this in Java with the following two-dimensional integer array. Each of the rows has a different length, but that's okay. Because remember, a two-dimensional array is an array of arrays, and as we said in the preceding video, there's no law that each subarray needs to have the same number of items in it. When you have an array with differing numbers of elements in each row, that's called a ragged array. Let's write a program to total up how many people gave their opinions in this survey. Here's our ragged array, and we'll set our total number of people to 0. Then we'll run a loop for each row in the array. For int row equals 0, row less than choices.length, row plus plus. The inner loop iterates over the columns. Now it's crucial to use choices subrow.length as our loop limit because each row's length is different. Inside the inner loop, we set the number of people to the number of people plus choices at the given row and column. And when we're out of the loop, we print the results. Let's save that, compile, and run it. And there's the answer. One final note. In this case, each row was one longer than the preceding row. But again, there's no law about that either. Let's switch these two rows. Recompile, and rerun, and it still works because we were careful to get the correct number of columns inside the inner loop. Let's take a look at this program that calculates the area and perimeter of two rectangles. We start with the methods that do those calculations. And then in main, we declare variables for the width and height of the first rectangle and print and calculate the area and perimeter. Then we set the width and height of the second rectangle and calculate and print its area and perimeter. There's nothing wrong with this program. It works exactly as advertised. But it's a bit clunky. We have the width and height as independent variables, and they're separate from the methods, getArea and getPerimeter, that work on them. Wouldn't it be nice if we could put them all in a box and tie it up with a nice neat bow? That is part of what objects do for us. They let us build a data structure where the related pieces of information, the width and height, are grouped together, and they allow us to group the methods that work on the width and height right alongside the data. We group things together in a class. Let's create a class called rectangle, which will go into a file called rectangle.java. In the class, we define the data that belongs to the class. A rectangle has a width, and a rectangle has a height. These are called the class's properties, the things that a class has. You may also hear them referred to as attributes or fields. Think of this class as a blueprint that tells what a rectangle is made out of. In order to make an object from the blueprint, you have to construct the object, in the similar way that you have to construct a house out of a blueprint for the house. To construct objects from their blueprint, you need a constructor. Constructors are very special. They look like functions, except they don't have a return type. Inside the constructor, you set the values for the properties. By default, a rectangle will have a width of 1.0 and a height of 1.0. You can also provide constructors with parameters. I can have a constructor where you tell me how wide and how high you want the rectangle to be, and I'll set the width to whatever you told me the width was, and the height to whatever you want the height to be. After I have the properties of the class and the constructors, I then put the methods, which are the methods that work on the data. I can have double get area, which returns the width property times the height property, and double get perimeter, which returns 2.0 times the width plus the height. We don't need any parameters for these methods. When they need to access width and height, they'll look at the properties, and they're right there because everything's all together in the object. Let's give it a try in the testrectangle.java file. Inside of main, we're going to construct a rectangle. It's like every other declaration we've done so far. We give the data type, in this case the class name rectangle, the variable name, R1, and on the right-hand side we initialize it by invoking the constructor with the new keyword. We want the new rectangle, and we'll use the default constructor. Rectangle is the class. R1 is the object. We also say that R1 is an instance of the rectangle class. Let's define another rectangle, R2, which will be a new rectangle with a width of 3 and a height of 5.5. Now let's call the methods. Instead of doing it the way we had to do it before, by saying r1.width and r1.height, namely the non-object way, instead we'll use the dot notation just as we used with strings to call the methods. We'll set area1 to be r1.getArea. You might want to read this from right to left. Invoke the getArea method using the data belonging to R1. And we'll have perimeter1 be r1.getPerimeter. We're telling R1 to invoke its getPerimeter method, or, again from right to left, invoke the getPerimeter method using the data that you find in R1. And let's print out the results. Let's save that and compile it. And let's run it. And let's do likewise for the second rectangle, which we'll do without intermediate variables. We'll print area and perimeter, and this time we'll tell R2 to use its getArea method, and we'll call the getPerimeter method for the object R2 to use its data. Let's compile and run, and that works as well. And that's a quick overview of objects. In the next videos, we'll go into more detail about classes, properties, constructors, and methods. In the preceding video, we went directly from a statement of the problem to the code. The design of a rectangle was sufficiently straightforward that we skipped the design phase. However, for any non-trivial program involving classes and objects, you really want to spend time designing them. And the vehicle for doing that is a Unified Modeling Language, or UML, diagram. At the top of the diagram, you put the class name. Then you list the properties and their data types. Unlike Java, the data type follows the property name. Finally, you list the methods for the class. Again, the return type follows the name rather than preceding it. You can also represent objects in UML format. Here are the two rectangles we created in the preceding video. For objects, you give the variable name and its data type, and then the values of the object's properties. We'll be revisiting UML diagrams and showing more of their features in upcoming videos. When we deal with primitive types like int, double, char, and boolean, the data is stored directly in the memory address for the variable. When we do this assignment, j is assigned k, the current value of k is copied into j's memory area. But when we create objects, the variables hold references to the memory area that contains the data. Now, what happens when we do this assignment that says R2 is assigned R1? The contents of R1 are not copied into R2. Instead, R2 is set to refer to the same object as R1. The area of memory previously referenced by R2 is no longer accessible. A process called the garbage collector will reclaim that area of memory to make it available for other objects to be allocated. Because R1 and R2 now reference the same memory area, this code, setting R2.width to 7 and then printing R1.width, will produce an output of 7.0. And here's the code to prove it. The takeaway from this video: primitives store their value directly in memory. Objects store references to the memory where the data is held. Here's the design for a class that keeps track of room reservations, with a room name and a day of the week from 0 to 6, with 0 representing Monday. Here are two reservation objects. Each one has its own room name and its own day number. Now let's say we want to keep track of the number of reservations we've created. The problem we need to solve is that there can be only one copy of this number. It doesn't belong to any of the individual reservations. In a sense, the number of reservations belongs to the class. To indicate that a property belongs to the class as a whole, rather than any of the object instances built from that class, we underline it in the UML diagram, and we use the word static when we declare it inside of our class. We'll have static int nReservations equals 0. In the constructor, we'll add this line, nReservations plus plus, to increment the number of reservations every time the constructor is invoked. Let's add some code to display the number of reservations. This doesn't need to be an instance method. It's accessing a static variable, not an instance variable, so it will be a static void method called show nReservations, and it'll print number of reservations created is, and then nReservations. Let's compile that. And here's a test program. This test program creates two reservations and shows each one. Then it calls the show nReservations method, the static method that belongs to the class. By convention, when you call a static method, you use the class name instead of an instance name to remind people that this method is static and it belongs to the class. Let's compile that, and let's run it. It's important to know that an instance method can access a static variable or method. For example, I can have an instance method called good, which will print the number of reservations, a static property, or call the static method. That compiles fine. It doesn't work the other way. If I have a static method, it can't access one of the instance properties, and it can't call an instance method. If I try to do that, I get a compile error that says a non-static variable or a non-static method cannot be referenced from this static context. Here's a table that summarizes access. Instance methods can access instance or static methods and properties because the static ones belong to the entire class. Static methods can only access static methods and properties. They can't access anything that belongs to an individual instance of the class. Here's another place we can use static variables to convert a day number to a day name. We can use a static array of strings called day name, and it'll have the names of the days of the week. It never changes, so it can be final. Now we can use it when showing a reservation. Instead of the day number, we'll put the day name for that number. Let's go to our test reservation, compile everything, and run it. And there's the use of our static array of strings. In summary, use instance methods and properties for things that differ for each object. Use static methods and properties for things that are independent of an individual object and belong to the class as a whole. Let's consider this code that creates a circle object with a radius property. We'd like to pass it to a method that will resize it by a given factor. Here's the code for that resize method. When we pass myCircle to the method, the reference to myCircle is copied into parameter c. Because both c and myCircle refer to the same object, when we update the radius of c and exit the resize method, myCircle will have its property updated. Just as we were able to update arrays in place, when you pass an object to a method, you can update its properties in place. And again, as with arrays, there's a school of thought that says you should not change the object in place, but instead always return a new value. That would mean returning a new object in our case. Here's the rewrite of our resize code to be a method that returns a circle object. As before, we create a circle in main, and as before, parameter c is a copy of the reference to myCircle. But this time, we create a new circle object with the updated radius and return that new object. A reference to that returned object is stored in newCircle, leaving the original myCircle untouched. So, which should you do? Update objects in place or return new objects? If you're in an environment where memory is at a premium and you don't need the object's original state, then you may want to update it in place. Otherwise, my personal preference, and it's a strong preference, is to return a new object. That way, you can call the function multiple times with the same input and not worry about whether the first call changed your object's properties in some unexpected way. Here are the first four elements in the periodic table. We can create a Java class to represent a chemical element. This class has no mutators because once you have created an element, its characteristics don't change. Here's the code for the element class. It defines the properties, the constructor, and all of the accessors. Here's a program that calculates the average atomic weight for the first 4 elements. It creates 4 new element objects, adds their weights together, divides by 4, and prints the result. Let's compile that and run it. And there's the answer. There's nothing wrong with this program, but if we had to do the average of the first 40 elements instead of just 4, the code would become a lot longer and a lot more difficult to write and maintain. Just as we used arrays to group together similar values, such as an array of ints to hold test scores or an array of double to hold an array of prices, we can create an array of element objects. We can say element array chemicals is a new element array of length 4. And now we can put the objects into the array. We can say chemicals sub 0 is assigned hydrogen, chemicals of 1 becomes helium, chemicals 2 becomes lithium, and chemicals sub 3 is assigned beryllium. Now we'll calculate the weight using a loop. The total starts off as 0, and for int I equals 0, I less than chemicals.length, I plus plus, we'll have total weight plus and becomes chemicals sub I dot get weight. For the average, we'll divide the total by chemicals.length. This gives us added flexibility. If we add more chemicals to the array, our code here doesn't have to change. Let's compile and run. This is some improvement, but not a great improvement over the original code. We can make our initialization a bit more compact by using braces to initialize. Instead of these 5 lines of code, we can say use braces to fill the array chemicals with hydrogen, helium, lithium, and beryllium. Let's compile it and run it. Again, it still works. We can also do the initialization directly without the need for our individual variables for hydrogen, helium, lithium, and beryllium. We'll put our declaration here. Element chemicals equals, and then in curly braces, we say that it's initialized with a new element for hydrogen, a new element for helium, a new element for lithium, and a new element for beryllium. And we no longer need our temporary variables. Let's compile and run. It still works. Finally, one more improvement. Because arrays of objects are arrays, we can use a for each loop instead of a counting loop. We can say for each element EL in the chemicals array, we'll take total weight plus and becomes that element's weight. Let's compile and run. And that works too. And that's what you need to know about creating and using arrays of objects. Let's start discussing object-oriented programming with something everybody understands. Toasters. In order to think in an object-oriented way, you need to think about the things an object has, its properties, and the things an object does, its methods. Usually we start out with properties. What does a toaster have? It has slots, 2, 3, or 4. It has a voltage, 110 or 220, a number of slices of bread currently in the toaster from 0 to the number of slots, an on-off switch, and a darkness setting, usually from 1 to 10, where 1 is death warmed over and 10 is cremation. And here's the corresponding UML diagram for the properties. In terms of methods, we have a constructor. The only two things we need to set ourselves are the number of slots and the voltage. We ship toasters with no bread in them, turned off with the darkness set to 1. We'll omit the getters and setters here, as there's nothing particularly new in them. What other things does a toaster do? You can turn it on or turn it off. That's the shorthand for set turned on to true or false. You can insert bread. The parameter is a number of slices to insert. And you can pop the bread out, which sets the number of slices to 0. And you can convert the toaster object to a string for display for the users. And here's the code, with the properties, the constructor, the getters and setters. And notice, by the way, that when I set the number of slots, I make sure that it stays in the range 1 to 4. And I make sure that the voltage is either 110 or 220. And then the extra methods that I talked about earlier, turn on, turn off, insert bread, and pop bread. And here's toString. Here's some test code. I'm going to create a 2-slot toaster that has 2 slots at 110 volts, and a toaster for Europe with 4 slots and 220 volts. I'll turn on the 2-slot toaster, set its darkness control to 4, and insert 1 slice of bread, and then I'll print out both of them. Let's see what that looks like. And there's my output. That's all well and good, but in reality, no manufacturer builds the entire toaster themselves. Instead, they buy the power supply and the dials from some other manufacturer and then put them into the toaster frame, which they themselves build. In an object-oriented world, we use what the book calls composition or aggregation to make classes or objects that are composed of other classes and objects. We'll create a power supply and a dial class. The power supply has the voltage and whether it's turned on or not, and it does the turning on and turning off. The dial has a setting, and we're adding a minimum and maximum value to make it more generally useful. For example, some companies might want to buy a dial that goes from only 1 to 4 instead of 1 to 10. Our toaster object will now consist of a number of slots and the number of slices of bread, and the power supply object will take care of the voltage and turning on and off, and the dial object will take care of the darkness setting. The only methods we now have for the toaster are the ones that involve the parts that the toaster company is responsible for, inserting the bread and popping it out. In the code, here's our power supply object with the voltage and its on or off status, the constructor, the getter and setter, and the turn on and turn off methods. Here's the dial class, which has its properties, constructor, and the getters and setters. In the toaster, power now becomes a power supply object, and darkness becomes a dial object. In the constructor, we must then create a new power supply of the desired voltage and create a new dial for the darkness. When we insert bread, we must first check to see if the toaster is turned on. We can't say get turned on because that method doesn't belong to the toaster. It belongs to the power supply, which is why we need to say power.getTurnedOn. Similarly, in toString, we need to get the voltage from the power supply and we need to get the setting from the dial in order to be able to use them. In main, we have an expression like this. Read from left to right, we're telling the 2-slot toaster to get the power supply object and tell it to turn on. Similarly, in this line, we're telling the 2-slot toaster to get its darkness object, the dial, and set its setting to 4. You will see this sort of chain of method calls whenever you have objects composed of other objects. In Chapter 11, we'll learn another way of adding functionality to objects, inheritance. While this book, and many others, strongly emphasize inheritance, current best practice says to prefer composition over inheritance. Here's a UML definition for a circle class that's part of a graphics program. It has a color, a boolean that tells whether it's filled or not, and a radius. It should also have a center x and y coordinate, but to save space I've omitted those. And here's the definition for a rectangle class. It also has a color, a boolean for filled, but this time it has a width and height. Look at all the fields and methods that they have in common. What if we were to add triangles, pentagons, and even more geometric objects? That would be a lot of unnecessarily repetitive code. We can avoid that repetition by using subclasses. We can create a class that contains all the common fields and methods and call it geometric object. This general class is a superclass, also called a base class or parent class. The circle and rectangle classes now contain only the items that make them circles and rectangles. They are subclasses or child classes, and they will inherit all the accessible fields and methods from their parent class. How do we implement this in Java? First, here's geometric object. It has its fields, its constructors, the getters and setters, and a toString method. Here's the circle class, where we use the keyword extends to specify that a circle is a subclass of a geometric object. The only thing that we're adding to the fields is the radius, the thing that makes a circle a circle. The color and filled fields are inherited from the superclass geometric object. We have the constructors, the getter and setter for the radius, and the area and circumference methods, and finally our toString method. Let's take a closer look at the constructor. It uses setColor and setFilled to access the fields in the parent class. Why didn't we use the fields directly? Since they're inherited, why didn't we just say this dot color equals white and this dot filled equals false? The reason we can't do that is because here in geometric object, they've been declared private. And that means that nobody outside the class that declared them can access them, not even a subclass. Let's compile and you'll see what I mean. And we get errors because color and filled have private access in geometric object. That's why we had to use set color and set filled, because those are public in the superclass geometric object. And now it compiles successfully. That's also why we have to use getColor and isFilled in the toString method. Let's take a look at the rectangle class. It again extends geometric object. So a rectangle is a subclass of a geometric object. We only need to specify the width and height, the fields that make a rectangle. And we have our constructors, the getters and setters, the area and perimeter methods, and toString. Here's a program that tests these classes. We'll create a circle, and we'll create a rectangle. We'll print them, which will invoke the toString method. For the circle, we'll get its area and circumference. And for the rectangle, we'll get its area and its perimeter. Let's compile and run. And there's our output. So far so good, but there's still some duplication of code. Here in the constructor for circle, we're calling setColor white and setFilled false. But that's the same code that's handled by the noArgument constructor for geometric object. And here we're setting color to color and setting filled to filled. But that's the same code that's happening in the toArgument constructor for geometric object. Java lets us call the superclass constructor by using the keyword super. In the noArgument constructor, we'll tell Java to call the noArgument superclass constructor. And here in the multiple argument constructor, we're going to tell Java to call the superclass constructor with the specified color and filled. When you use super, it must be the very first non-comment line in your constructor. Let's recompile that to make sure it works. Recompile test and run it. And it also works fine. We can do the same thing here in rectangle. We'll replace these two statements with a call to the noArgument superclass constructor, and these two statements with a call to the multiple argument constructor for the superclass geometric object. In summary, you can create subclasses by extending the superclass, and you can call the superclass constructor by using the super keyword. In the preceding video, we talked about using super to call the superclass constructor. Consider this chain of classes and subclasses, where brush is the parent class for toothbrush, and toothbrush is the parent class for electric toothbrush. Here's the code for the three classes. I've left out getters and setters to keep the code size to a minimum. The brush class specifies the color, and here are its constructors. Toothbrush extends brush by adding a bristle type, And electric toothbrush extends toothbrush by adding a battery size. One thing to notice is that in the constructors for electric toothbrush, I never call the superclass constructor explicitly. Similarly, in the toothbrush constructors, I never call the superclass constructor for brush explicitly. What happens here in testbrushes.java when I create a new electric toothbrush? Even though I've not explicitly called the superclass constructor inside electric toothbrush, Java implicitly will call that no-argument constructor for toothbrush. Toothbrush doesn't have an explicit call, but Java implicitly calls the no-argument constructor for its superclass. This is called constructor chaining. When we call new electric toothbrush, the no-argument constructor implicitly calls the no-argument superclass constructor. That's the toothbrush, and its no-argument constructor implicitly calls its parent class's no-argument superclass constructor, which prints out these words, zero-argument constructor for brush. Once that constructor finishes, we resume with the toothbrush constructor, and it prints zero-argument constructor for toothbrush. Once that constructor is done, it finishes the electric toothbrush constructor by printing zero-argument constructor for electric toothbrush. And finally, our new electric toothbrush has been constructed correctly. Let's run the program. And sure enough, that's what happens. What if we do this? If we say electric toothbrush, electric 2 equals new electric toothbrush, and we'll call its one-argument constructor with the battery size AA. And we'll put a dividing line in here so that we can distinguish one set of output from the other. Let's recompile, and let's rerun. Again, it calls the zero-argument constructor implicitly for the parent and grandparent classes. This brings up two questions. First, what would happen if we explicitly called a one-argument constructor? If here in electric toothbrush we called super with soft bristles for our toothbrush. The answer is that it would then explicitly call the one-argument toothbrush constructor here, which would again implicitly call the zero-argument constructor for the brush class. Let's recompile and rerun it. Our zero-argument constructor for electric toothbrush called the one-argument constructor for toothbrush, which implicitly called the zero-argument constructor for brush. Here's another question. What happens if there's no zero-argument constructor for one of the superclasses? Let's put everything back to the way it was. We're going to remove this explicit call to the superclass constructor. And here in toothbrush.java, we are going to comment out the zero-argument constructor so that it can no longer be found. Let's recompile toothbrush, and let's recompile electric toothbrush. And we get an error. The constructor toothbrush in class toothbrush cannot be applied to the given types. Java gets this error because it can no longer find the zero-argument constructor for toothbrush that it's implicitly attempting to call. What if we'd done it differently? I'm going to uncomment the constructor here. And now I'm going to recompile electric toothbrush. That will succeed. Now, again, I'm going to remove the zero argument constructor so that it no longer can be found. And I'm going to recompile only that class. What happens now when I run testbrushes.java? The answer, I get a runtime error telling me that there's no zero argument constructor for toothbrush. So no matter how sneaky you try to be to get around not having a no argument constructor, Java will stop you either at compile time or at runtime. That having been said, I would strongly suggest that you do not leave constructor chaining to chance. Instead, you should explicitly call the superclass constructors. This will avoid any possible compile or runtime errors from a missing no argument constructor. Let's look at the geometric object class again. I've added two methods, getArea and getPerimeter, to this base class. Both of these methods return 0. Looking at the circle class, I'm overriding those methods. In this case, the perimeter of a circle is its circumference. Here in rectangle, I'm also overriding getArea and getPerimeter to calculate the area and perimeter of a rectangle. Finally, I have a new class, triangle, which also extends geometric object and defines a triangle by the lengths of its sides. And here are the methods for calculating its area and perimeter. Now take a look at this test program. I'm going to try this. I'm going to create a geometric object called shape and assign it to be a new circle with a radius of 3, color blue, filled. Let's view our message window and compile this to see if it compiles okay. And it does. Why? Because circle extends a geometric object. Anything that's a circle is also a geometric object. This does not work the other way. If I try to say circle C equals new geometric object, the compiler will complain that geometric objects can't be converted to circle. That's because all circles are geometric objects, but not all geometric objects are necessarily circles. Now let's create an array of 3 geometric objects. Again, all of this is valid because a circle extends geometric object, rectangles are geometric objects, and triangles are geometric objects. I want some code to get the total area of all 3 shapes. We'll set double total area to 0, and then have a for loop which goes through the entire array, and say that total area plus and becomes shapes sub I dot get area, and then print the result. What do you think will happen when we run this program? You might be thinking that we'll get 0. After all, this is an array of geometric objects, and in geometricobject.java we've said that getArea returns 0. Let's compile this, and then let's run it. And it turns out we don't get 0. There are really 2 things that are going on here. Let's look at what happens when the compiler sees the Java code. As far as it's concerned, all the elements of shapes are geometric objects, and that base class has a getArea method. That's why the compiler doesn't complain when we say shapes sub I dot getArea. At runtime, things are different. At runtime, things are different. When the program runs, Java looks at the object that is actually stored in each array element. The first element is truly a circle, so circle's getArea method is called. The second element is a rectangle, and rectangle's getArea method is called. The third element is a triangle, and its getArea method is called. That's why the sum of the areas came up to something other than 0. This is called polymorphism, from the Greek words meaning many forms. In Java, polymorphism means that a parent class variable refers to a child class object. At compile time, Java sees variable shape as a geometric object, the parent class. At runtime, Java sees its form as a circle. Let's look at geometric object and its subclasses again. In addition to getArea and getPerimeter, which are overridden in each of the subclasses, I've added to each subclass a method that is unique to that subclass. Here in Circle, I've added a getDiameter method that returns the circle's diameter. That's sort of a useless method, but I needed something. Here in Rectangle, I've added a getDiagonal method that returns the length of the diagonal of the rectangle. And here in Triangle is a method that returns the opposite angles for all three sides as an array. Let's take a look at this test program. We already know that this is valid. I can set a geometric object variable to refer to a rectangle object because any rectangle is a geometric object. Because this is, at heart, a rectangle, what I'd like to do is show what its diagonal is. If I try something like this, double diag equals shape.getDiagonal, and then print the result, this will not compile properly. Because as far as the compiler is concerned, shape is a geometric object, and geometric objects don't have a getDiagonal method. To get around this problem, I can use a cast. I can say, shape is really a rectangle. I'm telling the compiler to treat shape as a rectangle, and rectangles do have a getDiagonal method. Now, when I compile, it's successful, and when I run it, I get the correct result. By the way, the outer parentheses in the cast are necessary to make the compile work correctly. Now let's look at this code. We have an array of geometric objects and a loop that prints out what each one is and its area and perimeter. This works fine because all the subclasses have overridden toString, getArea, and getPerimeter. It compiles fine, and it runs fine. What I'd like to do now is get the specific information for each shape. For the circles, I want to print their diameter, for the rectangles, their diagonal, and for the triangle, the angles. Unlike the preceding example, where I knew I had a rectangle, I don't want to write this program to depend on knowing in advance what kind of a geometric object each array entry will be. Here's the pseudocode for what I want to do. If the shape I'm looking at is a circle, then it's okay to cast it to a circle and call its getDiameter method and print that. This part I already know how to do. I can say diameter equals, do my cast to a circle, and then getDiameter. This will compile okay because I'm telling the compiler, treat shape sub I as a circle, and circles do have a getDiameter method. And now I can print it out. The question now is, how do I determine whether an object is a circle object, a rectangle, or a triangle at runtime? The answer is the instance of operator. If shapes of I is an instance of the circle class, this expression will return true, and it means I have a circle. If shapes sub I is a triangle or a rectangle, it's not an instance of the circle class, and the expression will return false. Similarly here, I can ask if shapes of I is an instance of rectangle, then it's okay for me to say diagonal is treat shapes sub I as though it were a rectangle with a cast, and then it's okay to have the getDiagonal method call, and I can print out the length of the diagonal. To save some time, here's the code to handle triangles. Let's compile, and let's run. And there we have each of the shapes with its area perimeter and its specific information: the diameter, the diagonal, and the angles. The takeaway from this video is to remember how polymorphism works. At compile time, whatever class you used to declare the variable is the one the compiler sees. If you want to use a method that belongs to a subclass, you must explicitly cast the variable to that subclass. But before you cast, you need to make sure that the object really is a member of that class, and you use the instance of operator to give you that information at runtime. In the preceding video, we used instance of to check an object's runtime type before casting it to the type we needed to make the compiler happy. You might have been wondering what the limits are on casting, if any. Let's find out. In this program, I've created a geometric object, a circle, and a rectangle. In this example, I'm taking the circle and casting it to a geometric object, which has a getArea method that returns 0. The compiler is happy with this. What's going to happen when I run this program? Am I going to get a 0, which is the result of geometric objects getArea method? Or will I get a number that's not equal to 0 because at runtime I still have a circle with a radius of 3? Let's find out. And the answer is you can't fool the Java Virtual Machine runtime. It knows at runtime that the object is still a circle, and it still calls circle's getArea method. Now let's try casting a superclass to a subclass. In this case, I'm taking the geometric object and telling the compiler to treat it as a circle and then do a getArea. Let's see what happens now. The compiler likes it. But at runtime, the Java Virtual Machine tells me that a geometric object cannot be cast to a circle. Finally, what happens when we try to cast one subclass to another subclass? In this case, I'm attempting to cast a circle object to a rectangle class. And the compiler will tell us, no, you can't do that. These are incompatible types. The moral of the story? Always use instance of to make sure that you are casting to an object's correct class at runtime. Up until now, we've been using arrays. They're very useful, but they have one problem. They have a fixed size. You have to know in advance how many elements the array will have. What happens if we need to have an arbitrary number of items? For that, we use an array list. Let's write a program that asks the user for prices until they enter 0, and then lists those prices as a percentage of the maximum value. To use array lists, you need to import java.util.ArrayList. To create an array list, you must specify the type of object that it contains, and that type must be a reference type. In our example, we'll want an array list of double objects with a capital D, because those are reference classes as opposed to small d doubles, which are primitives. You specify the array list type in angle brackets, and then you give the array list a name and say that it's a new array list. Use the angle brackets again and parentheses. If you want to, you can repeat the data type inside these angle brackets on the right hand side, but you don't need to. Here's a do while loop to read in the numbers until we get a 0, the sentinel value. We'll set a small d double, one price, to 0.0, and then put up the prompt and read the value. If the price is greater than 0, then we'll add it to the array list, and we'll do that as long as one price is not equal to 0. To add an item to an array list, use the add method. PriceList.add one price. Hold on, you might be thinking. Didn't you just say that we need capital D double objects inside our array list? But here you gave a small d double value to add. What's going on here? In a similar way that Java promotes an int to a double when one is needed, Java automatically converts a primitive to the corresponding object when the context demands it. In this example, the right-hand side, 29.95, is a primitive, and the left-hand side is a double object. Behind the scenes, Java is actually doing this. It's calling the value of method in the double class to wrap the primitive 29.95 as a double object. This conversion is called boxing. The reverse from an object to a primitive is called unboxing. In the second statement, we're multiplying dprice, an object, by 0.90, a primitive. Behind the scenes, Java is unwrapping the object, extracting the primitive value, and using that in the calculation. And that's why it's okay to do this. Our primitive one price is being put into a capital D double box, and the price list's add method is happy. Now let's do the rest of the calculations, but only if we really have items in the price list. We'll set the number of prices to be pricelist.size, and that's the method that tells how many elements are currently in the array list. If the number of prices is greater than 0, then we have work to do. Otherwise, the user didn't enter any data. We use the get method to get the first item in the price list as the current maximum value. We'll set double max price to be pricelist.get 0. Just as with arrays, the first item in an array list has an index number of 0. Now, go through the remaining prices to find the maximum. For int I equals 1, I less than n prices, I plus plus. If pricelist.get at that index value is greater than the maximum price, then the maximum price becomes that value. The next thing I'm going to do is go through the price list again and change it in place to percentages. I'll use the get and set methods to do this. Technically, I don't need to change the array in place. I could print out the percentages without storing them back in the array list, but I needed an excuse to show the set method. Let's go through the entire array list, starting at 0, and calculate the percentage of the maximum to be the price list item at the given index divided by my maximum price. And then I'm going to set the value at index I to that new value that I calculated. By the way, there's a lot of automatic boxing and unboxing going on in lines 36 and 37. See if you can figure out where it's happening. Now it's time to print out the results. And I'm going to use a different way of iterating through the price list. I'll say for double price in my price list system.out.printf. Let's use 3 places to the right of the decimal point and a percent sign. Because percent sign is special, it introduces formatting. To get a true percent sign, I need 2 percent signs in a row. And print the price. And then make sure that my output ends with a new line. Let's compile that. And let's run it. Let's say $3.95, $20, $17.95, $19.95, and $7.25. And then that's our last price. And there are the percentages of the maximum price. When you're working with array lists, get and set are the 2 methods that you'll use the most. The ArrayList class has other useful methods, but that's the subject of another video. Let's talk a little bit more about array lists. First, how do you convert an array of objects into an array list? Consider these 2 arrays of strings. The most direct way to convert to an array list is a for loop. I'll create a new array list of strings called chemList, and that will be a new array list. And then for each string, chemical inside the chemical array, I'll add it to the chem list. And let's print out the result. And there's our chemical list. Another way to do the conversion is to import java.util.arrays, notice the S at the end, and use its asList method to create a data structure to pass to the constructor. In this case, I'm going to have an array list of string called planetList. And it's going to be a new array list. Instead of empty parentheses, I'm going to call arrays.asList of planet array. And let's print that out. And there are my 2 lists. I'm going to switch over to the Java shell to show you the rest of the things about ArrayList in this video. Here's our chem list, and here's our planet list. To remove an item from an array list, you use the remove method and give an index number. That call will return the removed item. So if I say removed items equals chemlist.remove 2, the removed item is H2SO4, and that entry is indeed gone from the array list. You can also give remove an object as its argument, and the first occurrence of that argument in the list will be removed. This version of remove will return true if something was removed successfully, false otherwise. For example, I can say removed OK equals planetlist.remove Mars. That's true because it was in the list, and indeed it is removed. If I say removed OK equals planetlist.remove Saturn, that returns false because that wasn't in the list, and the planet list remains untouched. There is one situation where you can get into trouble with these two different flavors of remove, and that's when you have an array list of integers. Let's have an integer array, capital I because I need to have objects, and we'll set an array with the numbers 32, 19, 45, 25, and 60. Then I'll create an array list of integer objects, and it'll be a new array list that's based on my array. If I try to remove 19 from the list by doing this, I'll get an index out of bounds exception. This call to remove is trying to remove the 19th element of a list that has only 5 items in it. Java is not going to automatically box the 19 into an integer object because an unboxed int primitive is a valid argument to remove. In this case, what I have to do is explicitly convert the primitive 19 to an integer object so that Java calls the method that I want. Removed OK equals agelist.remove integer.value of 19. Now I have an integer object, and the 19 is gone from my age list. If your array list contains anything other than integer objects, you'll never run into problems with these two different versions of the remove method. A couple of other useful array list methods. Contains. I can ask planetlist.contains Earth, which returns true. Planetlist.contains Pluto returns false. Here's a list of names, and notice that Joe is duplicated in that list on purpose. The index of returns the index of the first occurrence of an object, or -1 if it's not in the array list. Namelist.index of Joe returns 1. Namelist.index of Norman, which is not in the list, returns -1. Last index of returns the index of the last occurrence of an object, or -1 if it's not in the array list. Namelist.lastIndex of Joe returns 4. And again, for a name that's not in the list, returns -1. And those are the other things that you can do with an array list. One of the key features of Java is the ability to set the accessibility, or visibility, of a class's members, its properties and methods. we've used the public access modifier to allow complete access to properties and methods, and private to allow access only within the class where the methods and properties are defined. Sometimes you need to adjust visibility somewhere between those extremes. There are 4 places where access can happen: access from the same class, access from a class in the same package, access from a subclass in a different package, and access from a different package entirely. The most visible and least restrictive option is public, allowing access everywhere. The next less visible option is protected, which allows access from everywhere except a different package. If you don't specify any access modifier, you get the default visibility. Class members are accessible only in the same class or the same package where they were defined. Finally, the least visible and most restrictive option is private, which allows access only from the same class. The book says it quite nicely. Use private for things that are not for use outside the class. Use public for things that are intended for people who are using the class. And use protected for things that are intended for extenders of the class but not users of the class. One additional note: if you override a method in a subclass, you can make it more visible. In this example, the child class makes its overridden version of a protected class public. However, you cannot make a method less visible. If you try to override a protected method and make it private, the compiler will stop you. And here, again, is the table summarizing the visibility modifiers in Java. Once again, here's a program that asks a user for their age in years and converts it to days. There's a while loop to make sure that the user enters a number that's greater than 0. Let's compile the program and run it. Negative numbers and 0 give us error messages, and positive numbers give us a correct result. It's still possible to make this program crash by giving non-numeric input. For example, if I put the word 20, the program crashes. In Java, we say that the program throws an exception. And indeed, if you look at the error message, you'll see that we have an input mismatch exception. Exceptions are objects in Java that give information about runtime errors. It's possible to catch these exceptions before they crash your program by using try and catch blocks. You put the code that might throw an exception inside a try block. And then tell what to do when you catch an exception that Java has thrown at you. You catch, give the name of the exception you're trying to catch, which is an input mismatch exception, and a variable in which to store that object. In the catch block, you handle the error. First, we're going to clear out the bad data from the input stream. We'll say input.nextLine. We're not assigning that to any variable. We want to take that data and throw it away. And then we want to print an appropriate error message. Please use digits only. One other thing we're going to have to do is we're going to have to import java.util.inputMismatchException. Let's recompile and rerun. Again, negative numbers and 0 cause errors, and now non-numeric input also gets caught without crashing our program. And positive numbers still work. Consider this program which asks for a dividend and divisor and calculates the quotient and remainder. There are two possible exceptions that can happen in this program. First, we could have non-numeric input, which gives us our input mismatch, or we could try dividing by 0, which would give us an arithmetic exception. Let's use try and catch again. We'll put a try block around the code that could be bad. And in our catch block, we will catch exception. That's the parent class for almost all runtime exceptions that we'll ever want to handle. And then we'll print out an error message. We don't need to import anything here. Exception is part of the java.lang package, and it's automatically imported. Let's recompile and rerun it. This time, if we use non-numeric input, it gives us an error. And if we try dividing by 0, we also get an error. While this works, it's not ideal. We'd like to be able to distinguish which exception we had and give an appropriate error message for each different exception. We can do that by adding two different catch clauses. We can catch an input mismatch exception and tell the users to please use digits only. And we can add another catch clause for arithmetic exception and print out that division by 0 is not allowed. We're going to have to import java.util.inputMismatch exception, but we don't have to import arithmetic exception because it's part of the java.lang package and it's automatically imported for us. The variable name that you use for your exception is local to that catch block. That's why I'm able to use the same variable name for all my catch blocks and the compiler won't complain about it. Java checks for exceptions in the order that you specify the catch blocks. When an exception occurs, Java will first check to see if it's an input mismatch. If it's not an input mismatch, it'll check to see if it's an arithmetic exception. And if it's not that, it'll try for the generic exception, which will catch just about everything else. Because exceptions are tested in the order you type them, you always want the most general exception last. Let's compile and let's run. If I put in non-numeric input, I get an appropriate error message. If I try to divide by 0, I get an appropriate error message. And good input works properly. And that's the basics of handling exceptions. The next few videos will go more in depth about the types of exceptions, how you can throw them, and when you should and shouldn't use exceptions. Where do exceptions fit into the Java class hierarchy? All exceptions are subclasses of the throwable class. One of its subclasses is error, which represents system errors, like these. If you ever get a linkage error or a virtual machine error, it means the system has some serious problems, and your best bet is to terminate the program as gracefully and quickly as possible. As a side note, I've been programming in Java for many years and have never encountered one of these. The other, more common subclass of throwable is exception. Most of the errors you've encountered this semester are almost certainly subclasses of runtime exception. Arithmetic exception is for things like division by zero. Null pointer exceptions occur when you try to use an object that doesn't reference anything. An index out of bounds exception happens if you attempt to access elements outside the bounds of an array. And illegal argument exceptions occur if you pass arguments to a method that it can't work with. All of these are called unchecked exceptions. You can catch them, but the compiler won't insist that you do. This is a good thing. Otherwise, you would have to put a try-catch block around every integer division and every array access in your programs. There are, however, exceptions that you must handle within your program. These are called checked exceptions. If you use a method that could throw a class not found exception or IO exception, the compiler will insist that you deal with it, either by catching it or throwing it to the method that called your method. We'll be seeing IO exception a lot when we talk about files later in this chapter. Let's talk about when to use exceptions and when not to use exceptions. Here's some code from an earlier video where I ask for the dividend and divisor and then calculate the quotient and remainder. This program uses arithmetic exception to make sure the program doesn't crash if the user tries to divide by zero. I feel a little bit guilty about having shown you this code because it's really misusing arithmetic exception. If I want to avoid that division by zero, I can just as well do it with an if statement and not have to do the extra work for both me and the Java virtual machine of setting up an exception and a try-catch block. Similarly, in code like this, where I'm using an index out of bounds exception to make sure that the user enters a number that's inside the array bounds, I really shouldn't be using an exception. When an if-else statement will do the job just as well. Why did I have them in the other videos? Because I needed an example, and those were the most directly understandable ones that I could use. What about the input mismatch exception? I'm keeping that one in both programs because testing for whether an input string is actually a number isn't something you can handle with a simple if condition. There's another situation where you want to use exceptions instead of if-else, when you're creating a library for other people to use. Consider this code that's part of an array utilities library. We have a max method that finds the maximum value in a data array. What happens if the person who's using our code passes an empty array into our max method? That's an error and we have to handle it. What we don't want to do is to put in an if statement that prints out an error message, because we don't know who's going to be using our library. Maybe they want an error message, maybe they don't. We also have to return some value. What should we return for an empty array? Should we return 0 as a result? No, again, we don't know what the user wants to do. Maybe they're using 0 as a sentinel value, and that would cause problems for them. In this case, we want the code to throw an exception. The user can then catch it and do whatever they want. Right now, the code throws an index out of bounds exception when given an empty array. We can improve on that by throwing an exception of our own. In the max method, we're going to put an if statement. If the length of the data array is greater than 0, we're good to go. Otherwise, we're going to throw a new illegal argument exception. When you create an exception, you can give the constructor a string with the error message that you want. In this case, we'll say the array length must be greater than 0. We'll also want to say that this method throws an illegal argument exception in case of error. You don't have to do this, but it's a good idea to make it explicit. Now, when we recompile and rerun, we still get an exception, but it's customized to help our library's users fix their error. In summary, don't use try and catch when an if statement will do the job just as well. When writing methods for other people to use, don't guess what kind of error processing they'll need. Throw an exception and let the users handle the error as they see fit. Until now, we've done all our input from the keyboard and all of our output to the screen. This input and output has a lifespan of the program. We'd like to be able to read our input from files and write output to files so our data takes a more permanent form. The Java file object gives you access to information about the file. If you want the contents, there are other classes that you use to do that. To access that information about a file, create a new file object with the file name or path name. There are two kinds of path names, absolute and relative. An absolute path name on Windows includes the drive name and is often written with backslashes. When you open a file using backslashes, you must use two backslashes in a row because backslash is the escape character for strings. You can use a forward slash as your directory separator if you prefer. Java will automatically fix it to do the right thing on Windows. However, it's better not to use absolute path names. If someone on Macintosh or Linux wants to use your program, it will fail because neither of those operating systems has letter-named hard disk drives. Instead, use relative path names that describe where a file is in relation to the directory where you have your Java source and class files. In this example, the states.csv file is in the same directory as the class file, so all we need to specify is the file name. The relative path to the names.txt file is a bit more complicated. See the link in the video description for a lengthier discussion of relative path names. Once you've created a file, what kind of information can you get about it? Here's a program that prompts the user for a file name and then opens a file with that file or path name. It then tells you if the file exists or not. This is the best way to find out if the user has entered a valid file name. You can find out if the file is a directory or a plain file. File.length gives you the size of the file in bytes. You can find out if you have permission to read the file or write information to the file. Did you use an absolute path name when creating this file? Is it a hidden file? When was it last modified? And what is its true absolute path name? Although you should avoid absolute paths, there will come a time when you need one, so you need to know how to get it. The file class also has methods to create directories, delete files, and rename files, but we won't go into those here. Let's run the program and try it on a few files. First, let's try something called nosuchfile.txt. It doesn't exist, so we're going to get a lot of false and 0 bytes. You'll notice on my full path name that I don't have a C drive. That's because I'm running on Linux instead of Windows. Let's try a file that does exist. States2019.csv. It exists. It's not a directory. It's a plain file, 923 bytes long. I can read it and write it. I didn't use an absolute path. It's not hidden. Here's when I last modified it. And here's its full path name. Now that you have a file object and you know how to access the information about it, you can use that file object to read and write the file that it represents. And that's the subject of the next videos. Here's a text file named prices.txt that contains prices of items bought on a fairly lengthy shopping trip. We're going to write a program that totals the prices, adds 5% sales tax, and prints the results. Here's the pseudocode. You may want to pause the video and analyze it. To read from a file, you create a scanner object based on a file object. Here's the code for creating a file, as we saw in a preceding video. We'll have a file called price file, and it's a new file, and the path name will be prices.txt. Instead of making a scanner based on system.in, we'll use price file. Our scanner, named input, will be a new scanner based on the price file. Unlike keyboard input, where we needed a sentinel value to tell us when we were finished with input, when using files, we can test to see if there's anything left in the scanner's input stream by using the hasNext method. HasNext returns true if there's data left to read, false otherwise. Reading a double is accomplished with input.nextDouble. And closing the scanner is input.close. Let's compile that, and we'll get an error. When you create a scanner from a file, it's possible that the file doesn't exist, and that's a checked exception. The compiler is telling us that this is an exception that we must either catch or throw to a calling method. Let's use try catch. We'll put a try block around the main logic of our code, and then we'll catch file not found exception, and when we catch it, we'll print out an error message. As long as I'm adding a catch block, I'm going to add another one for an input mismatch exception to handle the case where the file has bad data that can't be converted to double. We'll say that there's bad data in the file and print the exception. Before we can compile again, we have to import those exceptions. We'll import java.util.inputMismatchException and java.io.fileNotFoundException. Let's recompile and run it. And it works fine. If I change the name of the file from prices.txt to noprices.txt and then try to run the program again, I get the error that the prices.txt file was not found. Let me rename that to the correct name. And in here, let's put some bad data, like 2 point, and I'll use the letter O instead of the digit 0. Let's run the program again, and we get the bad data in the file. There are a couple of other points I need to cover. First, why did I catch file not found exception rather than using an if-else with file.exists? Doesn't that go against what I said in a previous video to use if-else in preference to exceptions? The difference here is that file not found exception is a checked exception. I must deal with it. I don't have the option of using an if-else instead of the exception. Finally, there's a change I would like to make to the code where I read from the file. Rather than reading token by token, it's preferable to read line by line. So instead of using next double, I'll have a string line and read the next line of the file. So I'm reading the file one line at a time, and I'll take that string and convert it to a double. When I use this technique, instead of an input mismatch exception, I will get a number format exception, which I don't need to import. I still have the bad data in the file, so let me recompile and rerun. And this time, not only will I get the name of the exception, I'll also get more useful information as to what caused the exception. Just to make sure that I haven't introduced any further errors, let me go back to the prices.txt file and get rid of the bad data and run the program again. And it still works properly. In summary, what you need to know about reading files from a Java program is to create a file object, make a scanner based on that file object, and then read it one line at a time and process the data on those lines. And remember, when building a scanner with files, you must have a catch for the checked exception, file not found exception. Here's a text file named people.txt with a list of names. We're going to write a program that reads in the names, puts them into last name first form, and writes them out to a new file. This program will need two files, one for input. File infile is a new file based on people.txt as the path, and file outfile, which is a new file whose name is switched people.txt. As we've done before, we need to create a scanner for our input file inside a try-catch. Our scanner input will be a new scanner based on infile, and will catch file not found exception. If there's an error, we'll print out the exceptions message. For output, we're going to need a new class called printWriter. We're going to create a printWriter named output, and it will be a new printWriter based on our output file. Creating a printWriter will also throw a file not found exception in case of error. That means we don't have to have another catch block. Here's a loop for reading the input. As long as the input has more data available, we're going to read one line at a time by using the next line method on our input scanner. We'll create a string array called nameParts, which will become the result of taking the line and splitting it on blanks. The new name will be the second name on the line, which is nameParts sub1, a comma and a blank, and the person's first name, which was the first item on the line. Instead of doing system.out.println to have output go to the screen, we're going to use the printWriter's write method. We'll have output.write new name. The write method, just like system.out.print, doesn't add a new line when it writes. If you want new lines in the file, and we do, you have to add them yourself. After the loop is finished, we'll close the input file, and this is ultra important, we have to close the output file as well. Why? Because disks are slow compared to the CPU. Instead of writing data immediately to the disk every time a program has something to write, Java maintains a buffer of data and fills it up as you write to the printWriter. When the buffer is full, it writes all of that data to the disk. The printwriter's close method makes sure that all the data in the buffer gets written to disk, even if the buffer isn't full yet. Let's compile the program, and let's run it. There's no output to the screen because all of our output has gone to a file. Let's open switchedpeople.txt, and here are the original names and the names in last name first form. What happens if we add a couple of names to our original list? Let's add Arturo Toscanini and Neil Sedaka. Save that, and we'll run the program again. This time, the file switchedpeople.txt already exists. The old version of the file is removed, and a completely new file with the same name is created. If I come here, it'll say the file switchedpeople.txt on the disk is more recent than the current buffer. Do you want to reload it? And when I reload it, there are Arturo and Neil in last name first format. Because opening a printwriter will wipe out an existing file, this is a place where you can use file.exists if you don't want users to overwrite a file that has already been created. One additional note: this program will crash if you add a blank line somewhere in the middle, or if you have someone with only one name, and it'll give incorrect results if you have somebody with more than two names. You might want to try fixing the program to solve these problems. The link in the video description will show you both this program and the solution. In summary, to write to a file, open a printwriter that's based on some file object. Use the write method to write output to the disk file. If you want new lines in your output, you have to put them there yourself. And always be sure to close your printwriter before your program ends. In the preceding video, I emphasized that you have to close files when you're done with them. Not only is it good programming style, it's necessary for making sure that your output buffer gets written to disk. Still, it is sort of busy work. There's a way to avoid this busy work. Try with resources. Take the code that creates the scanner and printwriter, your resources, and enclose it in parentheses before the opening brace of the try block. Make sure you use parentheses or it won't work properly. Once you've done that, you no longer need to explicitly close the resources. As soon as the try-catch block is done, Java will close them for you. Here's our code for switching the last and first names, and we're going to convert it to try with resources. We'll put our resources in parentheses and then the opening brace of our try block. And let's indent it properly as well. We can now get rid of our input.close and output.close. Save, compile, and run. And there's our file with the names in last name first order. It still works. The book says that a try with resources doesn't need a catch clause. Let's put that to the test by commenting out our catch block here and recompile. This time we get an error. Why? Because opening resources from files can generate checked exceptions, and those must be either caught or thrown. Since we haven't caught the exception, we have to say that our main method throws file not found exception. This is what the example in the book does. Now it compiles. But if I make the input file unavailable by changing people.txt to nopeople.txt, and I run the program, the exception will get thrown to main, which can't handle it, and the Java virtual machine crashes our program. The moral of the story: use try with resources to have Java automatically close files for you. And use a catch block, even if technically you don't need one.